almost to lunch. We have one talk, and then we will have a big lunch break. There's lots of great places nearby. It's a beautiful city to explore. Who's here in Atlanta for the first time? Awesome. How many people are here in the US for the first time? Very few. Yeah, I don't know that I would travel into the US this year. Like it's a very crazy time to be here. Yeah. All right.
Can we start in
About 5 minutes.
5 minutes? Cool.
Actually, about 7 minutes.
Okay.
So make sure you're drinking water. It's humid here. It's beautiful. It's a beautiful city, but it is a little humid.
Yeah.
This is one of the great American cities that really shows its fall colors. So when you're walking around this year, you really get to see all of the different colors of the trees, like out front and everything. It's really gorgeous. Not every city in the U.S. is like that. I had a wild experience thinking of seasons. I was actually just in New Zealand for the first time in my life. I don't know, has anybody been to New Zealand? New Zealand is an amazing place. I grew up in Hawaii, and I was really struck by how much the vibe of New Zealand is like the vibe of Hawaii. It was very surprising to me. But the other thing that really was cognitively, giving me some trouble was I know that Australia and New Zealand have opposite season from us. In my brain, I know that. But to be walking around in New Zealand in September and seeing all of the pine trees putting out that little brand new green bud and all of the other trees that are just beginning to bloom and all the brand new lambs, and I'm like, this is wild, right? Like actually seeing physical evidence and connecting that with your brain, Like I remember as a kid in Hawaii, there were a lot of people that I knew that were into surfing would talk about endless summer, and I don't think I ever really put together what that meant. Like you could actually go and be in summer somewhere in the world all year round. Like it just never really connected for me until just this trip to New Zealand.
We are ready?
You guys want to start a little early, or we got about 5 minutes, but I'm happy to let you go ahead and get started. All right. Let's get going here. All right, Artem and Matthew, take it away.
Thank you. Thank you very much. Thank you for joining us for our talk today. Before we start with the talk, just 1 or 3 quick questions, something like this. How many of you already have built an IDP or platform, or however you call it internally? How many of you are already using Crossplane? How many of you are already starting to using Crow, the new kit on the block, Kubernetes Resource Orchestrator, or play with them? Okay, get it. A few. Cool. Thank you very much. And welcome to our talk. Our talk will be a tough one, how to make the dev pain go away with the right level of abstractions for your platform. And before we start, a short introduction about ourselves. Mathieu, can you...
Hi, everyone. I'm Mathieu Benoit. I'm a platform engineer. I'm also a Cloud Native ambassador and a CNCF Sandbox project score maintainer. I'm glad to be here with Artem and you all.
Yeah, short to me, obviously. My name is Artem Laiko. I'm a head of platform engineering for IITS Consulting, a startup from Germany, founded 2019. I'm CNCF certified kubestronaut, also platform engineering ambassador and co-published author of the book Implementing GitOps with Kubernetes. If you start to build a platform, in the most cases, you will get in touch with GitOps. But enough about us, what you have to expect from the talk today and what not.
Yeah, actually, what we want to cover is what we have learned, listened, and also experimented while building platform. And when you build internal developer platform, there is always needs. There is pain points to resolve. There is more collaboration to have. And what we want to highlight today and illustrate is what is the right level of abstraction for your developers or any technical stakeholder with your platform. And we don't have the answer. And we won't answer literally for your own needs, your own business, your own company, your own developer, your own platform, right? But we want to show some example with tools that you could use to fit maybe the right abstraction for them, right? The goal is to show this combination of tools with live demo, right? So we hope you will enjoy this.
Medium, it's have something about 30K. Some AI started to scrap it. They're not the real numbers. It's about 30K views, about 11K reads, so read ratio about 40%. And someone has put it on Reddit and to see also what the community think about it. And yeah, I mean, if we are starting to build a platform in the most cases, we are speaking about abstractions.
Yeah, exactly, Artem. So some of you are building a platform like you answered earlier in the introduction, and you know your question, one of your questions is, when people are interacting with a platform, what is the right level of abstraction? And some people love abstraction, but some people hate abstraction. And you may have different audience, different customer, different expertise in front of you. So there is this double-faced coin that in the comment was illustrated. Could you illustrate that?
We are here, we are listened, and we are not judged. So we are just showing you the one abstraction. You can see the one side, keep this man away, they're meaning me, from my code. And also, no crow, again, YAML over YAML, the developer should YAML. This is the one side. And then you have the other side, they really recognize the value of abstraction if you're doing the right way. As you can see, yeah, abstraction is the right way. A lot of people also say, yeah, the right way, but you presented the wrong solution. It's true. I mean, at the end of the day, you need to know your platform, you need to know your team, you need to know the skill set. But like I say, we are here, we are listened, and we are not judged. So we just presented you the both sides of it. And I guess, I mean, at the end of the day, if we start with abstraction...
That's the reality, right? You have your own tool. So we will present Crow and Score, but maybe someone will say, hey, I'm using Helm and Crossplane and Terraform. Yeah, sure. Just bear with us with the concept and the approach, the iteration you may have and you may want to do as well. Because at the end of the day, we need to step back. It's not about tools. It's about pain points. So you should ask yourself, what are the pain points you are solving? What is the business outcome for your platform and for your developer at the end of the day?
Yeah, like you say, it's about the pain point to solve it. And if we are just taking a look at a simple web application, you will see here, for example, that we have, a simple web application consists of manifests like HPR, service, deployment, ingress, service account, and all the stuff. On it, and so on and so on, and the most developers are not aware of it, and we are just speaking about a simple web application here. You have API, you have gRPC services, you have different types you want to deploy. Inside the class, as a managed service, you need to care as a developer more and more about the manifest you're using. We are not speaking about tool here, and we are not starting to speaking about the SBOOM stuff and everything coming for us in the next year. This is the reality we see. But Mathieu, you are working about, I don't know, now 5, 6, 7, like
infrastructure. And here we will use KRM, so the Kubernetes Resource Management.
Solution is okay for you?
Is it big enough on the back?
That's okay. Thank you very much. So we are starting just with a demo, and the first question is, of course, like Matteo already explained, we just first wanted to going away with the abstraction from the developer with Crow to compose just a simple Kubernetes native manifest for a simple generic web application. But before we are starting, for example, why we are starting to using Crow, or what is Crow? And we really like it because with, give me a second, I guess it should be like this one. We really like it because you not just only can, it's not just because it's a new kit on the blog starting last year, but you can also do something like you can define your own resource graph definition, like your graph, not just only for Kubernetes resources, but you can do things like this. You can say, first please create a VPC, then create an IAM role, and before you're creating an AKS cluster, you can fetch the output, and then you can use this output by creating it. It is really mighty, and also really nice because it's a lightweight if you compare it with another tools. So this is why we like Crow and another, but this is just to giving a short introduction. We start, but we're starting slow. So we're starting with compose just Kubernetes manifest. And our demo or overview looks like this one. As platform engineer, we're defining a resource graph definition, which create for you a custom resource definition. It's a really nice way to create a custom resource definition by not creating one. So then, as a developer, we will use the same type or kind from workload and creating a custom resource, and then Crow will handle all the magic for us, validate it, and create all the stuff. Our setup running on kind, we will share the demo after it with you so you can directly starting and explore it by yourself. So this is because we are choosing kind. And yeah, let's take a look at the, now we impersonate the platform engineering view, and let's take a look at the resource graph definition, how it looks like. You define here, for example, the kind, we call it workload type, then you can define some specs, you can define some default values, you can also already create everything you need, or setting some values, or set its requirement from point of EU platform that the developer need to put in or not need to put in. You can also overwrite it or let it overwrite it by the developer. You can also create your own types and then create, for example, here, if you're looking at port, you can create your own type port, and then you can create kind of an array or a new specification of it. And this is how the resources like. Here we are starting to define the graph. And if you're looking here at the resources, we have, for example, the ID, and let's take a look at the role. It makes more sense. Here we are saying, first the role must exist, and then you can creating a role binding to it. This is how you define the dependency tree. And like we already said, we want to go beyond the basics because the most use cases you see in the internet and a lot of talks just giving you an introduction. And we wanted to see the limits of Crow and also see what we can do with Crow now, and the community is evolving. So for example, we are using it here for deployment part where we configure already best practices from the market. For example, we setting the security context with some default values, but allow the developer to overwrite it. You can design how you want it, but yeah, this is how we are using the resource graph definition from the point of the platform engineers. And let's take a look at the point of the developer. Very easy. You define your custom resource from kind workload. You just need to set a name and an image. We also put some more, like environment, because this is a reality. The developer want to set some args, some environment, and so on. But in the most cases, as a developer, you just need to define, I don't know, 7 lines, and everything, if you're doing it right, will be covered for you. And yeah, let's take a look on the whole picture. Again, we're zooming a little bit out and see how we're bringing Argo inside with. This is familiar to you. The only thing changing now, we are using Argo to deploy it, doing all the boring stuff. And Crow will create and evaluate then the manifest for this generic web application. We are using pod info from Stefan Prodan because you will understand it in a few minutes why we are using it. And let's just deploy it, really boring. We are doing here, we are doing, for example, git add, git commit, git push, and then Argo doing it behind the scenes. So we want to keep it boring for this part because it's not part of our talk to present how GitOps works. I guess most of you will be familiar with GitOps. And let's take a look what's happening behind the scenes. We can see here we have a new kind workload already active. We have a pod info running on it. We have a service, we have a deployment, we have HPR, we have everything from 7 lines. This is how you can design it. And yeah, I mean, that
So
is,
just with 5 lines as a developer in my workload manifest,
yeah, 7.
you
but
are
yeah.
generating all of that, right?
Yeah, you're generating all the, as you
Thank
can
you.
define. Thank you very much. And yeah, let's jumping. Now we have composed the deployment or a simple web application, but now something coming in and say we want to use, for example, infrastructure parts because our application running with databases, running with caches like the Redis cache. So we want to add it. And this is the next demo where we are speaking about standardization of the infrastructure to allow developer to use also parts like in-cluster Redis. And this is how it looks like. Same picture, familiar for you? The only thing we are doing it, we are adding Redis running inside the cluster. This is what you mean by inner loop in our case, something like this. So yeah, and let's take a look how it looks like from the developer. We impersonate now again the developer point of view. And the developer just need to say, I wanted an in-cluster Redis, true, enable it. And if you provide, for example, pointing out to it, you provide a documentation for self-service, how can they consume this custom resource. They also need just to pointing out to this one, adding a new arguments for that. So that's it. And if you don't believe us, let's just doing again the boring deployment, for example, again, git add, git commit, git push, argo cd sync. And yeah, hopefully, let's see. You can see it's starting to deploy here already a Redis instance. So just by the developer saying we wanted to enable, and now this is the reason because we're using pod info, because pod info you can run it with a cache. And we like it to show it as a developer by adding 2 lines. You also enable now a cache inside the cluster, but this is not only the things because we are wanted to going beyond the basics, and we say what is about if we want to running a managed service outside the Kubernetes cluster, and let's take a look how it looks like. I mean, same picture, we just exchange the icons from running in cluster, we are running on GCP, over the Kubernetes config configurator using behind the scenes to creating a managed Redis. So this is why we like tools like Crow, and let's take a look from the point of the platform engineers, what we need to add. And as you can see here, we're defining just a new ID and saying memory store, this is how we call it, and then some Google GCP specific values like memory size and so on and so on. This is the point from the platform engineering, and we need to do the heavy lifting. And from point of the developer, it's a little bit much easier. They just need, again, line 7, say now we don't want having an in-cluster Redis running, we just wanted a memory store Redis running on GCP. And they need to provide, again, in line 9, the cache server. And here is how it's solved, or here it's coming like as a platform team. You need first now create the managed Redis instance, and then you need to fetch the value of it and provide it in calm way, in a way to the developer. And here how you can solve, you can create a secrets behind it. The developer just need to point out to it, because at the end of the day, you can't pointing out in your custom resource to a resource which doesn't exist at the moment. And so you can create a secret pointing out to that, and the developer behind the scene it will create. It's take about 10 minutes, creates a managed Redis, putting the host name in the secret, and the developer just pointing out to it. This is how you can solve it, but this is also not anything. We have also other opportunities. I don't know if you like this way, how you can solve it, because it's a little bit static in this, how we solved it or how you can solve it. And Mathieu, will you tell you more about why score coming now in and how you can overcome this a little bit?
Yeah, because here, I mean, what you just demonstrated is very awesome. As a developer, I'm now defining my workload. It's a generic workload. I don't know for the people who has played already with Crow, but here we are not having a pod info container or website container or front-end, back-end. We have a generic workload definition, right? It was 500 of lines, and now anyone, back-end, front-end, website, API, pod info could use this, right? Which is quite generic and very interesting here. But we have faced some, not limitation, because Crow is also young and the community is very active, but we have seen some opportunity, because now the contract between the developer and the platform is a Kubernetes API. What if I have some breaking change as platform engineer in the API? Yes, I could change the first line with some API versioning to avoid breaking change. But what about this flexibility on top of this definition? So for example, how I could inject dynamically the output of the memory store, because when I will deploy the memory store, it will take some time. I need to grab the host IP address, host name, username, password generated. So with Crow, that's wonderful because you could inject that, waiting for that and inject in config map or secret. But after that, how seamlessly and easily I could here, and sorry, I could inject in my environment variable. There is a couple of ways to achieve that, but what we have seen is that we could add a templating templating tool on top of that to have this buffer between the contract and the developer. Because also here you have seen in cluster Redis true, memory store true. But what about if, hey, I just need Redis, right? In dev, please save me some cost and do that in cluster, fine. But staging, QA, and prod, I want in memory store, in GCP, in AWS, in Azure, because more secure, more robust, whatever the reason. The point is, now my file is environment agnostic or it's not environment agnostic. So what we did is this layer on top of this to add this flexibility and adding a little bit more of abstraction. Before showing you this, we just want to have the basic about score. It's kind of the same principle and approach with Crow. You have a spec on the left for the developer perspective. They describe what they want, their workload, their dependencies. And at the end of the day, it's generating via this core Kubernetes implementation, for example, generating manifest. And the platform engineering is responsible to generate the contract. What is the actual Kubernetes manifest? Is it deployment, job, workload we just defined, and how to actually provision a Redis? Oh, you are in dev environment? Let's do in cluster, et cetera, et cetera. You are in staging and prod? Let's do the Google Cloud way to do that, right? So Score is a very a good fit with this landscape of how we could have more abstraction from the dev perspective. So here, what we want to show you is in this giant workflow, we are adding 2 layers. As platform engineer, at the bottom of this picture, I'm, yes, configuring Argo, Crow, and my workload, CRD and RGD, resource graph definition in Crow. But I'm also defining a layer on top of this in order to define, hey, what are what we call score provisioner for Redis, for Postgres, for MySQL, and name it, right? That's still the platform engineering side. On the developer side, we have now also a layer between the dev and the contract, which is a Crow spec. And now the developer is not editing live and directly the Crow file, but will edit and author and be responsible of the score file. And that's where we will see how we could generate the actual Crow RGD behind the scene. So here, if you are not familiar with Score, that's a basic Score file to illustrate the Redis example we just showed earlier with Artem. But here, what's interesting is, so it's pretty much familiar to you with the Crow resource definition we showed you, right? If you see, there is similarity. It's YAML, and there is a generic approach with image, command, variables. But you could see that at the very bottom, there is this notion of, hey, I need a Redis. I'm not telling you in cluster or memory store, for example. And by the way, when you will here provision a Redis, please inject the associated output of this Redis. Again, what's the host, what's the username, what's the password. And then it will be reused and injected in my environment variable, et cetera, et cetera. So here, that's how now the developer will have a contract with the platform. So what we want to show you as well, on the platform engineering perspective, there is no magic here. You will have, like you have the definition of your Crow RGD workload with 500 lines. Here now, you keep that, but you have this layer. You remember when I mentioned the provisioner layer for the platform engineer? Here, that's where we have seen some use cases iterated through a list in Crow. It's not yet as robust as we wanted. The conditional aspect in CRO is at the top, at the resource level. We got some use cases where we needed more granular conditional templating. And that's where here you have a score provisioner templating to put together as platform engineer. And you map and you translate the score file to the CRO workload resource definition, right? And here, if you're familiar with Helm, that's Go template, that's Go function, that's Helm function. That's the same approach here, where you could have range, if then else, more granular to generate the actual workload spec. What we want to illustrate now is in action using the CLI, the tool, Score Kubernetes Generate. How I could generate from a score file to this CRO workload. My platform engineering are just defining this template you could see here, right? So I'm generating the manifest. Guess what? It will be this CRO workload, right? So locally, I'm generating the file. Again, I'm authoring the score file as a developer. It's generating the workload. And you could see similar stuff we just saw earlier, right? But here, what we want to show you is the same flow, right? The goal is to say, hey, now I have this file, the workload definition, CR, and I want to deploy it. So still using GitOps and doing this continuous deployment way. And here, same approach, right? We are in another namespace, and other namespace, and we have our pod info, and we have the Redis, et cetera, right? So same approach injected here. So with this layer of abstraction, what we have seen is deploying to Kubernetes is good, right? But sometimes it's kind of complicated to set up locally. Yes, you could use, like we are using Kind cluster, but are you asking your developer to have Kubernetes cluster locally? Maybe, and that may be good. But is it adding more complexity and cognitive load? Sometimes yes, right?
And you're relying on a controller running in your cluster if you want.
Exactly. So that's a possibility. But what we have seen also is, as a developer, I don't have Kubernetes, right? And sometimes if my Kubernetes is in GCP, AWS, or Azure, maybe I will wait for the CI/CD to tell me that my container is not running as unprivileged or doesn't have the connection string to the Redis. And it's adding delay, it's adding friction, it's adding iteration. So how we could shift left kind of this test. If my container is not running as unprivileged or not talking to Redis, I should know locally as a developer. So here we have yet another opportunity with this core abstraction. Why? Because now you could say with this exact same score file deployed in Kubernetes via CRO, I could also deploy via Docker Compose or Podman Compose, right? So here we will have still the same score file, you remember, and here we could do score compose generate. You remember the score Kubernetes generate to workload Kubernetes CR. Now we are taking another CLI to generate the compose file. Should I author the compose file as developer? Maybe, and maybe not, because here I have a seamless experience to generate a compose file locally, right? And here, guess what? I could do Docker Compose up. My pod info and my Redis will run locally, and I could test my application locally as containers without any Kubernetes involvement. So that's what we wanted to show you today.
So you define one specification running on both environments, same file.
Exactly.
So
So
do you call it workload specification for, or how do you call it in Score? Define one workload specification, or how do you call it? What is the name?
One spec to deploy them all or support them all. We hope you enjoy the demo. You got the journey and the different iteration on that. We have some recap for sure. I think we are out of time, or we still have a couple of minutes.
We don't have a lot of time, but in short, just giving you a wrap-up or a recap. As you can see, abstraction can having both sides. in the most cases, you need to understand the pain of the developer, and then you need to solve it, because if you try to solve your platform problems, you don't getting an adoption rate. And we love to over-engineer stuff. I'm speaking for myself, so yeah. And in the most cases, yeah, you need to listen to your developer. And if you're combining the right tools, I mean, it looks maybe you have a lot of complexity, but if you combine the right tools for the right use cases, you can achieve really nice abstraction. And yeah, and also, I mean, I guess it's a fact. A lot of developers I'm working with, they also want to run the stuff locally on their machines and test it in container and not deploy everything on Kubernetes. And yeah, like I say, also have some customers, they don't have even Kubernetes. They're using tools like Portainer running on-premise and running on VMs. So you can combine both worlds. It is a really nice way. You can, of course, using also on other tools. It's not we're saying you should use Crow and Score. You can combine them depending on what you like. And yeah, outcome and learnings we shared. We also share a lot of learnings, and we provide all our learnings and all the limitations we found out with Crow. Maybe we did it wrong to the community and also to the contributor. We are working on it. It's also you can find everything in this resource. If you're going to the demo repo, you can go into the learning stuff. Maybe we understand Crow on different on some spaces or some pieces wrong. It can also be possible, but we wanted to share our learnings, also then to get an exchange with the community and understand if there is a right limitation, because I also know that colleague from mine working also on Crow, and they say wait for the version 0.6, and a lot of stuff will be already solved, but it's not about this. It's just, yeah, give it a try and tested it, and yeah. And if you have more questions about Score, you can visit Mathieu at the kiosk on Wednesday at the Score kiosk between 2 and 5. If you want to grab a free copy of this book, you can coming to the vCluster booth at Tuesday. And I know it was a lot, but thank you very much for your time, and we really value your time, and we will really appreciate if you give us feedback, if you have some feedback for us. And so hopefully we can deliver something return on invest for your time, because I mean, if you are looking at the count here and multiply it with the time, thank you very much in short.
Thank you, everyone.
Yeah, we have a couple more. We have a couple minutes for questions. Anybody have any questions? Do you guys want to take some questions?
Yeah.
Please. Yeah, yeah.
Thank you. So, I like the Reddit post that in your ideal world, we should give developers Heroku style experience, or they should know about YAML, they should know about Kubernetes. What's your take on this?
I can start you.
Yeah, please.
At the end of the day, that's a good question. Should they do YAML, right? And I think you need a contract, right? At the end of the day, is it a UI? Is it a Slack message? Is it ServiceNow ticket? At the end of the day, I have a request. I'm a developer, and I need to self-serve, maybe, or deploy this application, right? So at the end of the day, you need to find a contract, and mostly out there, it's YAML file, but if you have other solution or a way to do that, I think go for it. You need to understand what will be the simple way for your developer to consume your platform, right? So my take is YAML is not bad. It's a contract. If you want to do something else as a contract for self-serving and automating as much as you can behind the scene, go for it.
I have a similar opinion that I working with different customers, with different developers, with different skill set, and I said our contract is to read and understand YAML. Not to understand all the stuff, but they should read it, because at the end of the day, if you're using Kubernetes and you're having the Heroku experience, it's really nice to start, but after you want to scale, and the most enterprises I'm working with, they have, I don't know, they have infrastructure, shadow IT, legacy stuff you don't want to see, but this is the reality, and then you need also to educate them, also to getting some like a try. So it depends on the customer. In the most cases, for me, works out to saying, let a common understanding of YAML, and this works very well.
Okay, and one last one. If we were living in a world where everyone is using Crow, projects like Terraform will no longer be needed, or or we will replace in Terraform with projects like Crossplan, Crow, and anymore.
Can I start as well, or do you want to start?
Yeah. I like the flow, so please.
So good question about Terraform here. And I think what Crow is bringing is a gap between, I have some manifest in Kubernetes to describe my container at the end of the day. And maybe there is ingress, HPA, network policy, etc. But we are missing the infrastructure dependency. And with Helm or other, you need to ask your developer or your CI/CD pipeline to provision infrastructure via Terraform, via ClickOps, whatever. But you need to inject the values of the output of this into your manifest, Helm chart, or environment variable. So Crow is a good fit to resolve this, hey, please figure it out in one pipeline, and avoiding the pain point of the iteration, how you inject, et cetera, et cetera. So Crow has a good way to do KRM, which is Kubernetes of Terraform. And you are asking me to do KRM and Kubernetes way, and I know it's too familiar to point of view. Yeah, Crow is eventually to say, hey, you don't need Terraform here because we are solving something else.
I have a little bit different opinion on that. I wish we can replace Terraform. I'm working with German hyperscaler or European hyperscaler, so it's very difficult because you don't have the provider for crossplane, and you need for Crow write your own because Crow using the Azure Service Operator, KCC, ACK, the this operator-driven, and I really love it for OpenShift 4. I'm speaking about OpenShift 4, and I really love this operator-driven approach, but the market was not ready. And they're doing the Kubernetes way on OpenShift 4, and I hope now we will be well educated, and I think this is the way to go.
In your security, I will ask them to migrate all the Terraform investment. No way. They will push back and they will help me to fail my own platform. Yeah. So Crow or like Crossplane are not a good fit here because you didn't listen to your other tech stakeholder, right? So in this case, like I have a lot of Terraform, maybe don't invest here, right? Because you will fail. You will satisfy the dev, but if the infrastructure is like, no, it's not compliant because you are not going through that, you are failing. So, yeah, it's, yeah.
Tough times. All right, well, thank you very much.
Great presentation.
We are now on our lunch break. We're going to come back at 2 o'clock. That's about an hour and 45 minutes from now. There is still a sign-up sheet out in front for lightning talks. That'll be happening tonight at 5:15. Have a wonderful time.
Testing, 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 testing.
Are we live? Okay. Hello, everyone. Welcome. Hope you had a good lunch and you're ready to. He's going to building Kubernetes.
Cool. Thank you all so much for coming. Very excited to be here. It's my second Rejekts, and I really love it. So, like we said, we're going to be talking about. I thought the title said something about AI in there. I don't know what happened. These might be the wrong slides. We're just going to go with it. I promise I'll talk about AI on every single slide as much as I can. This is exploring graph-based approaches to synthetic trace generation in Kubernetes, which definitely has things to do with AI. A quick round of introductions. So most of the stuff I'm talking about today, I didn't do any of the work on. This is work that my business did with Harvey Mudd College, which is a small science and engineering school in Southern California. They do a senior clinic project every year. So every undergraduate there does a clinic project. And this is the team that I had working with me. So I'm David. I'm up in the upper right. The faculty advisor was Prof. Beth Drukowski. And then this was my team from last year. So we have Saya, Henry, Karina, John V, Max, and Baltazar. Most of the interesting work that happened was done by them. Most of the boring stuff is on me. So just as a quick plug for the clinic program, if you're ever looking for really, really smart, motivated undergrads to help you out with hard problems, come talk to me afterwards. I'm happy to tell you more. So the problem, right, I'm supposed to talk about AI. So the problem is that training agents to operate Kubernetes is expensive. This is a chart that you probably can't read, but this is showing monthly Kubernetes-related spend in 2021. Something like 10% of companies were spending more than $1 million a month on Kubernetes-related costs. And it turns out that, like, if you want to train a machine learning agent to do something, you need a lot of data and a lot of time. And ideally, you want to be training on something that sort of looks like your production data so that they don't make mistakes and do bad things. And so that's going to get really expensive really fast. So this is maybe old news to everybody in here, but what's expensive about Kubernetes? I kind of think about Kubernetes as being split up into two components. You've got your control plane, API server, controller manager, scheduler, all of that stuff. It's expensive, but it's not ridiculously expensive. And then you've got your data plane, which is where all of your pods and all of your nodes and everything run. And that's where things get ridiculously expensive. So one of the tools that I've been working on for a long time is called SimCube. I've given a bunch of talks about it. Maybe you've heard of it, maybe not. The idea is that you can simulate out your data plane. All of the nodes, all of the pods, all of that stuff is fake. And then you can run a real Kubernetes control plane on top of that. And you can learn things about your cluster. This is a really quick architecture diagram of what this looks like. So in your production cluster over here on the left, you've got this component that's called the tracer. It sits there and it records events of everything that happens in your production cluster. You can save parts of that as a time series database, or sorry, as a time series file, and then you can replay that trace in your simulated environment. There's a bunch of details into how this works. I'm not going to really go into the details there. I have other blogs and other talks that talk about that. The important thing is that your simulation environment is cheap. Just to give a quick idea of how this works, like what is actually being recorded, this is a high-level representation of your trace file that comes out of your production cluster. We've got events, or we've got cluster states A, B, C, and D, and then we've got events that are transitioning between them. And our trace is this sequence of changes that happens to your cluster. So you can think of like A, B, C, and D. These are deployment objects in your cluster. Maybe they're scaling up and down. Maybe some other, like a new application gets deployed. Your old application gets rolled out to a new version, something along those lines. All of these things are the types of events that are getting stored in your cluster trace. That gets saved to a file, which you can then replay later on in your simulation environment and see what happens. This has a bunch of uses. For example, you can troubleshoot incidents, you can perform capacity planning, cost forecasting, a bunch of cool stuff like that, but we're not here to talk about any of that today. We're here to talk about AI. Yeah. So one thing that I think is kind of interesting is we've got this relatively inexpensive environment that you could let your machine learning agent just go play in, and it would be relatively safe and isolated and inexpensive. And so I've been wondering for a while, and I know some other folks have been thinking about this as well, can we do some sort of reinforcement learning-based approach using a environment like SimCube to train agents to operate on your Kubernetes clusters. That seems cool, but that's not what this talk is about. This talk is about the second question, which is anytime you do any sort of training, you need an enormous amount of data to do that training, and where does that data come from? So let's think about where can we get some data. So my clinic students this last year developed a tool called skgen. What skgen does is it takes a small set of data that you get maybe from your production cluster, and it bootstraps that into a large amount of data that in theory is somewhat representative of what your production cluster actually looks like. And so for the rest of this talk, I'm going to be really focusing on what is skgen actually doing. So there's kind of 4 steps, which I've outlined here. There's your construction, your expansion, and then we go through a phase called contraction, and then we actually generate more data at the very end. The interesting 2 steps are in the middle. This is where we do our expansion and then our contraction. And just as fair warning, this is all graph theory, so I'm going to try to make it fairly accessible, but if your background isn't in graph theory, I'll do the best I can. Please ask questions at the end. All right, so first step is construction. This is actually easy. We've already solved this problem. You've got a production cluster, you collect some data from it using the SimCube tracer. Done. We've constructed our initial data set, and we're going to use this to bootstrap everything else. So let's think about expansion now. So if you think about Kubernetes, you can imagine its state space where a state or a node in the graph is a configuration of all of the objects that are deployed inside your Kubernetes cluster. So your deployments, your replica sets, your stateful sets, your daemon sets, all of those things form this massive state space. And every transition between one state and another is represented by an edge in this giant graph that we're building. So if your deployment scales up from 1 replica to 2 replicas, that's an edge. If it scales up from 1 replica to 10 replicas, that's an edge. If a new deployment gets created, that's also an edge. You can imagine that this space gets very large very fast. But once we have, at least in our heads, in our minds, constructed this gigantic state space from Kubernetes, then we can start asking questions about it, like what nodes are actually visited inside this graph? What are sort of the most common spaces or paths that we take as we navigate through this graph? And I think one of the interesting things here is this is going to be unique and different for every single Kubernetes cluster, every single organization, because everybody does things just a little bit differently. And so one of the key insights that the team and I had last year is if you're trying to train a agent, some sort of AI or something to operate on your Kubernetes cluster, there's probably not a one-size-fits-all solution here. It's probably going to need to take into account some features or some factors about your specific environment. And so how can we sort of capture those features, those facets of your environment? My voice is a little rough today, as I'm sure you can hear, so I'm doing the best I can. All right, so we've expanded out. We've created this gigantic graph, this gigantic state space that encapsulates every possible Kubernetes state that you can imagine. How are we going to make that useful? Because we just got a graph that's way too big. So this is where the third phase of our approach comes in. This is the contraction phase. So again, we want to generate synthetic trace data. This is definitely an AI talk, so we're generating this trace data so that we can train AI agents. We're going to use this thing called graph contraction. This is a process where we take out an edge from the graph, and then we collapse the vertices that the edge connects into a single vertex. And so this is a way of shrinking the graph. And the question is, can we do this contraction in a way where we don't lose any critical information? And it turns out the answer is yes, using this thing called contraction hierarchies. And before I define exactly what a contraction hierarchy is, there's kind of this interesting pattern where you can imagine that there's multiple ways to get from one state in the Kubernetes graph to another state. That's sort of represented here. We can start over here in the state where your deployment has 4 gigs of RAM and it's got 3 replicas. And maybe eventually we want to get over here to this state where your deployment has 16 gigs of RAM and 4 replicas. And you can see there's a bunch of different ways that we can get through that. But it turns out that maybe the path you take doesn't matter that much. Maybe it's just the starting state and the ending state that matter. Because when you're operating Kubernetes, you're not going to go through all these intermediate states. You're not going to bump your memory and then bump your replicas and then bump your memory again. You're just going to do both of them in one go. And so the key insight that we had is that there are some states in the graph that are important and others that are just kind of transition states. And so if we can figure out where the important states are, then maybe we can do something interesting or useful with that. We actually saw this. Again, this is a chart that you probably can't read. I don't care about the numbers on there, but we did some analysis. There's a bunch of public data out there from Alibaba, from Google, from Microsoft Azure about what their distributed systems actually look like. And so we were able to do some analysis on some of those publicly available trace data to kind of confirm that yes, there are specific buckets and specific states that are in these graphs that are more frequently visited than others. And so this sort of confirmed that in theory at least, this idea has some merit. And so how does this work? So contraction hierarchies is actually a thing that you use on your phones every day. It's a way that Google Maps makes it easy to do shortest paths through a road network. Because there's hundreds of millions of roads that you could take, maybe thousands, I don't know how many roads there are. There's a lot of roads. Running shortest paths on all of those roads is going to be time and cost prohibitive when you're trying to get real-time navigation. And so when you're doing this sort of Google Maps type approach, they contract away all of the uninteresting roads between where you're starting from and where your destination is. One of the cool things about this approach is that it preserves a bunch of important qualities like edge weights. In Google Maps, your edge weights might be how long does it take to drive across this particular road. In this approach, what we're more interested in is probabilities, like how likely is it that we transition from one space to another. And we can do that using contraction hierarchies in an edge weight preserving, probability preserving way. And that's really cool. So in this graph, we've got our starting state with the green flag up here. We've got 3 potential ending states represented by the red flags there. What we're going to do is we're going to assign a weight to every single node in the graph. So we've assigned weight 1 to all of these intermediate states. We've assigned weight 2 to this center state. And what this indicates is that somehow that central state is more important than the intermediate states. And so what we're going to do is we're going to contract away all of the less important nodes. We're going to replace it with this graph. This is a lot easier to reason about. Now we could even do this one more time if you wanted, and you could say, okay, well maybe that middle state isn't even all that important. So let's just contract those away, and we can go directly from start to finish. You can kind of apply this process iteratively as often as you want to until you get to a graph that is sort of manageable. So we've done construction, we've done expansion. I just showed you how to do contraction. So what about the last step here? The last step is, well, now we've got this contracted graph. How can we generate new data out of that? So just as a reminder, in our contracted graph, we've identified, and you can identify this by looking at sort of, probabilities or statistics from your real production data, like these sets of nodes are the highest priority nodes in our graph. These are the ones that we visit a lot. All of the other nodes in the graph that are down here somewhere, we don't visit those very often or at all. So we contract away all of that stuff, and now we've got this hopefully manageable graph that is somehow representative of your production infrastructure. We also have done this in an edge weight preserving way. And again, edge weights are just sort of probabilities. It's like probability of transitioning from state A to state B. And so now we can generate new data just by doing random walks. So this part's easy. And we can generate as many random walks as we want and then bootstrap a small set of initial data into a huge amount of data that somehow looks like your production infrastructure. That was a lot of graphs and math. So what did we do exactly? And yeah, this is a talk about AI. This is definitely a talk about AI. So what I've shown, or what I've hopefully convinced you, is that we can take, again, we can take a small amount of production data that we collected from SimCube, or even just from your Prometheus metrics, or wherever else you want, and we can turn that into a huge amount of data. And you can use that data for anything you want. You can use it in like your CI pipelines to test your custom controller or something like that. Or you could use it to train an AI agent. And just to reiterate sort of the big idea that I pitched at the beginning of this talk is your infrastructure is your infrastructure. It's not anybody else's. And so anything you do, whether that's AI or your CI pipeline or whatever else, anything that you do is going to be very sort of specific to your environment. And so you want data that represents and reflects what your environment looks like. And so I'm going to close this out by just asking the question, what's next? I don't know what's next for AI. I'm not qualified to answer that question. But in terms of this project, there's a couple things that we want to continue doing. One is we've evaluated the effectiveness of this technique on some small clusters and some small trace data. We've also looked a little bit at some of this public data sets that are published by Azure or Alibaba. But there's a huge range between the small, like, toy things that we've run and Alibaba or Google. And so we'd like to be able to sort of evaluate the effectiveness on some of these, like, medium-size clusters and medium-size environments that are out there. And then the other thing that I have another clinic team that I'm working with this year, is we want to actually turn SimCube into a training arena that not just me, but like any of you out there could like download and install and try out your new fancy LLM or AI agent or whatever it is that the cool kids are playing with these days. So this is pretty much everything that I have to talk about today. I hope that that was interesting and useful and definitely about AI. There's a couple resources on here. You can learn more about SimCube there. You can read some more information on my blog. And if you go to that QR code, there's a blog post version of this talk that you can read as well. So thanks so much for your time, and happy to take any questions.
We have some minutes. Okay.
One thing you talked about was using contraction to create a state graph that is manageable. What goes into establishing what is manageable, and is that kind of like a trial by error thing, or there's some specific heuristics you're following?
Yeah, I mean, it's a trade-off. Sorry. It's really a trade-off between the fidelity that you want in terms of like these smaller states, like how many of those do you want to keep around, and how much memory you have. So it's kind of up to you. You can, like, that's a tunable threshold.
Anyone else? We have some more.
An AI ML person, so I haven't trained any agents. I'm trying to build the environment that we can use to train agents. My understanding is this sort of like starting with something generic and then like using an environment like this to sort of augment or improve is an effective way of doing this sort of training with a little bit less data, but that's not something that I've specifically tried on my own.
Thank you. Great presentation. This is probably like a sort of an open-ended question, but I was curious, like what look-back periods did you use to
data sets that we have from Alibaba and Google. These span, I think the Google sets are a couple months worth of data. Alibaba, I forget, is a little bit less than that. And then sort of like the toy problems that we were looking at, that's like, an hour or so of data. So there's a big range in terms of the amount of data that we have available. And I think, again, this is sort of like a tunable threshold that you can look at in terms of the more data you have and the longer that it runs for, probably the higher fidelity you're going to get out of your simulation or your training environment. Thank you so much. I also have stickers if anybody wants stickers.
35? Back.
All right, I think we are ready to go. Welcome everybody. We have on stage Brandon and Rim. They're going to talk about what Homebrew did to overcome the CI challenge, right? Yeah,
Yes.
thank you.
Yeah. Hi, folks. I'm Brandon Valentine from WorkBrew. With me is Ren Oliver from Mac Stadium.
Hey, everyone. Nice to meet you.
So we're going to talk to you for a little bit today about Homebrew. Homebrew is one of the most active and largest open source projects on the planet. And with that comes a really complicated CI picture. So Ren is going to talk a lot about what Mac Stadium has done to help the open source project manage that problem. I'm here really to set up the problem and talk to you about it. And I'm going to acknowledge right now we got the venue wrong on this slide, and I've already been called out on it, so we'll move on. So we're going to sort of go through a few different parts of the talk here. We're going to deliberately leave some time for Q&A at the end, so please save your questions. And I'm just very briefly going to introduce WorkBrew. How many of you in the room use Homebrew, have it installed on your work computer? How many of you have someone in IT or security who's a little bit grumpy about the fact that you have it installed on your work computer? So we are a very small startup trying to solve that problem. Our mission is to make it so that developers don't lose access to this tool. So if you want to introduce those grumpy IT and security people to me, I will be happy to make them less grumpy. That's really all I want to say about that, except to show you that we can do things like this for your security folks across an entire fleet of Macs that have Homebrew installed. There is a demo URL here at the bottom. If you want to book some time to talk to me about it, we'll happily make time for you. But let's talk about Homebrew now. So all of you know Homebrew, you know how popular it is. It's been around for 15 years. It has everything under the sun in it. Literally everything under the sun. There's 15,000 packages and growing. I think we're about to crest 16,000 any day now. And it's everywhere. There are 35 million devices checking in with GitHub telling us they use Homebrew on a daily basis. Those are just the ones that are permitted to check in. So I'm going to guess most of you on your work laptop are not reporting your Homebrew usage to GitHub. There's probably something in the middle on your network that is preventing that from happening. So who knows what the true installed base for Homebrew is, but it's massive. But the defining characteristic of Homebrew, the reason that it won, the reason everyone in this room has it installed, is that it really, really works as an open source project. It changes constantly. This is a snapshot of 1 month of 2025. Over 3,000 merged pull requests just in the Homebrew core repo. This is the repo that holds all the formula for Homebrew. So with that comes some really unique CI challenges. So Homebrew supports several major versions of macOS, currently all the way back to macOS Sonoma in 2023. And every single package in Homebrew has to be tested on every architecture and every version of macOS that is available. So currently that's Intel and Apple Silicon. And so when you think about 15,000 packages and you think about all of the different places those packages have to be tested, the problem adds up quickly. In fact, it's the dependencies themselves that really create the scale. So this command up here on the slide, this is me asking Homebrew how many packages depend on OpenSSL. So every time OpenSSL is bumped in Homebrew, 2,200 other packages have to be rebuilt. You can see very, very quickly what this CI bill must look like how much compute time must go into making it so that you can just brew install Python and not worry about it. This is a snapshot I took this morning, and you can see that the most recent job for rtab map, how many of you even know what that package is? I don't know what it is. It took over an hour of wall clock time to rebuild all the bottles for that package. So imagine what the bill looks like for OpenSSL. It's pretty insane. If any of you had a CI job that you ran every time you merged a pull request and it took over an hour, you would have some really, really uncomfortable conversations with management about the compute time that you're requiring for that job. So Mac Stadium has helped the open source project do something about it. I'm going to turn over to Ren to talk about what they've done.
Hey, everyone. Thank you so much for letting me speak with you today. My name is Rin Oliver, and I am the product manager of DevOps and integrations at Mac Stadium. So I'm here to talk to you about building macOS golden images with Packer and Orca. And so basically, automation makes everybody happy. Without automation, we're just lost. And manual macOS setup is a pain. It's really time-consuming. Takes a while. If I had $1 for every time I heard it worked on my machine, I'd be rich and I wouldn't be standing here right now. So onboarding of new devs takes days, takes weeks, depends on who they are, if they're offshore, if they're onshore. Either way, this takes forever. Nobody likes that. So basically, how Orca and Mac Stadium are helping to solve that is by building base images and golden templates with our Packer integration. So that brings us infrastructure as code for the macOS ecosystem. And what that looks like is Packer providing that single source of truth and the image configuration. Orca manages virtualized macOS environments. So if you've got macOS and you want to run it on a VM, that's where we come in. So it's Kubernetes orchestration at scale, providing that compute layer, and integrates natively, like I said, with Packer via that Orca Packer plugin. And with those, creating a golden template helps you eliminate that configuration shift. It really eliminates drift across your teams and provides a foundation for rapid provisioning of developer environments, means that people can get started faster and get back to work. So basically, starting point is how this all works is you start with a macOS base image, and you can find those on Orca Hub over at Mac Stadium, so orcahub.com. Go check those out. We've got Tahoe, we've got Sonoma, we've got Sequoia, whole bunch. Those are provisioned, ready to go. And our Packer plugin, which is open source, connects to the Orca API, spins up a temporary virtual machine from that base image, executes provisioning steps in sequence, and then validates all of those were installed successfully. And then that resulting image is saved as a new template, tagged with version, tags your metadata, and then it's available to deploy across your infrastructure. And then from that, you can spin up identical developer environments, meaning that everybody can use the same thing every time, keeps it consistent, and make sure that you don't end up with that, well, it ran on my machine, which makes your life a lot easier. So that's where Homebrew comes in. And you might be wondering, okay, what does that look like? What is it in Packer template? Why do I care? Why do I need one? So when you go in and you look at a Packer template, those are HCL files. And basically, those are going to look something like what we see on the screen here. What we've got here is a provisioner step running a shell script. And what that's going to do is it's going to basically use Homebrew to install things like Fastlane, Git, CocoaPod, Swift, things that every macOS developer needs in their toolkit to make their lives easier every day when they go to work. So basically, that source block, there's a source block, it's the first step. Source block, without that, you're not doing anything. Having these steps in sequence is very important. You start with your source block, you go to your variable block, then you go to your build block. So that source block has your Orca configuration, got your endpoint, got your credentials, selects your base images. For example, if you want Sequoia, you want Tahoe, that's where you put all that. Get your VM specs, configure your network, all of that. Your variables are your environment settings, credentials, secret management, makes that all reusable. In your build block, that's, like I said, these provisioner steps. So those are going to copy your config files. And the order of operations matters. It's basically like PEMDAS, like we were in school. So if you don't have it in the right order, you're going to run into bad times. So make sure that if you are writing one of these templates, that you have everything in the right order. So you want to install Homebrew first, and then everything else comes after it. If you need more tools, it's basically like YAML. You can add, you can take away. Whatever you need, you can add it using Brew. Like Brandon said, there's over 15,000 packages in there. If you need something added to your Packer template, if you need to take something away, feel free. These are very extensible, very customizable. So basically, that's what's inside that box. And it allows you to customize that golden image and really build out a developer toolchain that suits your needs. Makes your CI/CD life easier, makes it easier for your employees to run their virtualized Kubernetes infrastructure, especially on macOS. So basically you can run, Homebrew, Git, Xcodes, CocoaPods. Basically 90% of your macOS, iOS developer needs going to be covered with that golden image. So by putting it together with Homebrew, Packer, and Orca, you've extended that out and you've made your life a lot easier. So basically, like I said, the installation sequence really does matter. And so that's what's in that provisioning script. Make sure that you can run everything at the same time and make sure that all of those steps break down one after the other. And it's really similar to YAML. The order of the steps matter. if anybody here has seen a YAML file in Kubernetes, the order in which your job kicks off really makes your life a lot easier. So these are also really quick. You need about 15, 30 minutes, maybe less, to unlock the power of, just run Packer build, and then you'll get real-time output and validation through each step, really just virtually right in your terminal. And you can watch that build, and then using Orca, you can actually deploy an image straight from the Packer template, and then you're ready, you're off to the races. So, but if something goes wrong, don't worry. That's okay. Things go wrong all the time. We're developers, we know things go wrong. So that provisioner step, if something fails, it stops the build. Those VM artifacts are deleted so they're not taking up space on your system, and you've got some detailed logs there for troubleshooting, which is fantastic. So you might be saying, okay, why does that matter? Because, like I said earlier, these things take time. If you're setting this up manually, it takes 4 or 6 hours. Nobody's got time for that. If you're doing this with Packer, you've got a ready-to-code deployment ready in about 10, 15 minutes. That's a lot of cost savings. It's a lot of time savings. It means that you're not sitting there doing things individually, installing them step by step, waiting for things to pull down. You can just run Packer build and get ready to go. It's also consistent. Everybody gets the same tooling, same versions, same configuration. It works on my machine, it works everywhere. So it means easily reproducible builds for CI/CD every time. Also makes your life more flexible, makes it easier to adjust to things on the fly. By updating that golden image, you can roll it out to that whole team. A/B testing different versions, experimenting with new tools, everything is risk-free. You can roll back to previous image versions as needed, which makes your life a lot easier, and it means that you can do more things with less time. So also improves your developer experience. Means that your devs aren't going to be sitting there trying to set up their environment, and they can focus on doing the thing that you pay them for, which is writing code, instead of troubleshooting failed homebrew installs, pulling new flasks, etc. So that makes that onboarding step really self-service, and it reduces the amount of support tickets that you're going to have to put in, which means that you're not going to have somebody walking you through, how to install a package today. It makes your life a lot easier when you're going to work. So if you want to get started and try this out, you absolutely can. Feel free. We have the Orca macOS DevTools Packer template. You can check that out by searching Orca Packer integrations, and it'll pop up. It is open source. And then the Orca Packer plugin is also open source. Feel free to check that out. Our Orca Hub has our open source images at Orca Hub, and we'd love for you to take a look at those as well. And you can get started with Orca Desktop for free. And we'd love it if you had some Q&A. If you have any time, we can answer some questions. Thank you again.
Yeah, thank you, Ren. Just for context, before Mac Stadium did all this work to make it possible to virtualize these workloads, homebrew maintainers were literally buying stacks of Mac Minis and shoving them under their desk at home. And the fact that this is now repeatable and virtualizable is such an insane improvement.
Absolutely. One of our open source maintainers that I've worked with is Randy from DDev, and Randy has a ticket open, I think still, in the DDev repo that says, please get these Macs out of Randy's living room, because there's an entire server structure is in his living room. So with things like Mac Stadium, you can have that you can abstract that away, and you can have it virtualized, running on a VM, run that CI job, instead of having it in poor Randy's living room. Hi, Randy. So.
Yeah, here, let's give you a mic.
Who's first?
First of all, that model of a Mac Mini under everybody's desk sounds great to me. Isn't that distributed computing? Isn't that what we're here for? But actually, I was kind of wondering.
Yeah, we'll also just do Git between all those Macs as well, right? It's distributed version control.
No, BitTorrent. BitTorrent, come on.
There you go.
I was kind of wondering, as you're going through the process of setting all this up, my own experience is there's always a problem that you sit there and you beat your head against it for 3 months or 6 months, and then finally you go, oh, wait, this is actually very simple. What kind of issues did you have like that, or if you would just want to pick one during this whole process?
An issue that I had actually when I set this whole thing up was that sometimes for example, the steps matter. The steps really do. I had something backwards, and I had the homebrew install step running in the Packer template after I tried to install all of the happening was just that I was running into issues with building Tahoe because Tahoe was so new at the time I was working on this. I was trying to build out that template to bring that Tahoe dev kit to Mac Stadium so people can use it with our Packer plugin. And I had just was like, it might work. And it turns out that it did, but I was the first person to actually get Packer to run a Tahoe image for our customers. So that was really cool. And now they can use that and they can build out that Tahoe base image with these wonderful tools such as Homebrew and Xcodes and Swift and Fastlane, and makes their lives easier if they're devs working on macOS. So.
Maybe a related answer. Yeah, so at Workbrew we have sort of a version of Homebrew's CI that's running around our product to make sure that basically we're not breaking the Homebrew experience for our users. And having worked on that, one of the things that's really tricky about it is that you need Homebrew to bootstrap Homebrew. like at this point, it is how you get the build tools installed in order to build Homebrew. And so making sure that you have a stable version of it to begin with in order to build the newer version is really important. And there's also a bunch of prerequisites that have to be on the Mac that Apple does not make easy to get on the Mac, including the Xcode command line tools. That is actually, when you're talking about virtualizing a Mac, a big pain. Apple assumes that you're going to install it interactively by opening Xcode and going to a drop-down menu. That doesn't work if you're trying to automate.
The CI workflow for Homebrew and Workbrew kind of internally to be able to do this at scale and testing. But then you open the talk talking about IT, the relationship between the IT department and me as the dev. Just want to make sure I understand, is the model you're advocating here with what you described with Orca and Packer and Homebrew, is that I would, as the dev, I would just receive my endpoint from IT and then just deploy and work in that virtualized environment, and then just leave my endpoint just kind of IT managed? Or is there a model where I can just
Mac Mini under someone's desk model. And so I think what Mac Stadium has done an excellent job of is their stuff actually connects in to GitHub as a check runner for a standard CI job. And so they have an API with Orca that lets you demand a particular macOS image be stood up, and then those tests run in that image. And so what's amazing about the Packer stuff is seconds matter when you have a consumptive billing model and you're running a CI job where your startup time is something that you're paying for. And so this Orca Packer integration lets you cut out all of that startup time.
We have time for another question. Anyone? No? So thank you very much. Oh, we have one? Yeah, sorry. I was too quick to say thank you.
I've done a lot of research on virtualization.framework over the years, ever since
they're doing that. So that'll be interesting for folks because we know that there's probably millions of machines running Intel on Macs, and I don't know what their plan is for that. So that's going to be interesting. But here at Mac Stadium, we've got images all the way back for a while. We support right now a few base images. We support Tahoe, we support Sequoia, we support Sonoma, and beyond that, we've got a full compatibility matrix on our website. Please do check it out. we're trying every day to continue to bring more base images to folks. And like I said, if
Homebrew, and the internet is mad about it. Like, the GitHub comments are pretty spicy.
time, so I'm going to go ahead and start here. Hopefully this is working. This sounds like it's working. Okay, hi everyone. I'm Marina. I'm going to wait for you all to quiet down. But we're going to get started here just about now. Yeah, hi everyone. I'm Marina. I'm a research scientist at Adara, and I'm going to talk to you all today about inspiring identity, using Spire for verifiable container isolation. So getting right into it, this is kind of the question that we want to answer today. So you're running an application in a remote environment. How can you prove that it's actually in an isolated container? And the inspiration for this question came when I was doing some research in confidential computing. Because in confidential computing, one of the things that they provide is this idea of remote attestation, where you can, before you send your data to a confidential compute node, you can perform this remote attestation process to prove that you're actually going to send the data to this confidential compute node, and then you can encrypt it per node and kind of send it there. What I kind of want to look at is, what if we could do this without the kind of hardware piece, right? If you don't need the rest of confidential computing, how can we still get this proof of where you're running your containers and your applications? So for a little bit of background, I work at this company called Adara. We have a platform that it runs a type 1 hypervisor, which means kind of a hypervisor that can run directly on the hardware. And on top of that, we run root hardened zone. This is a lot like the kind of control zone of it. And on top of that, we run applications inside of what we call zones, which are basically just like kind of micro VM-like environments where you can run applications with kind of true isolation. So like you're not having any shared kernel state between different applications. A lot of what I'm going to talk about here kind of applies to any type of micro VM-like environment. I'm using this one because I work there, but yeah, anything where you're trying to prove the same kind of properties will apply to kind of what we're talking about today. So kind of given that as a tiny bit of background, what we want is proof that a workload is actually running in one of these zones, right? In one of these isolated environments, and not just kind of on some random compute node. And to do this, we're going to want to assign a cryptographic identity to the workload, right? This means that you can encrypt data directly to that workload and do all kinds of other cool stuff. And because we have this kind of hypervisor-based model already, we want to kind of root the trust for this system in that trusted hypervisor. Because kind of the whole idea of using micro VMs in general, right, is that you're reducing your trusted computing base, right? You're reducing the amount of code that you have to trust. And so we want to keep our trust small, even while we're adding this feature. And we want to do this in a way that can work in distributed systems. So it's not just that you can encrypt stuff, when you're working on your own local machine, but no matter where things are running, even if they're running on different hardware in different places, we want this all to still work. And then finally, we want workloads shipped without secrets or key materials. Right, one way to do this is just to put a key in every application that you ship, but then you have to manage all those somewhere else, and this kind of can become a huge pain. They often get leaked. All kinds of stuff goes wrong. So when we were talking about this, what we really realized is that what we need is spiffy, right? We were talking about these requirements internally, and we're like, well, someone's already done a lot of this work. And so kind of looking at the mapping, what we're looking for is to create a system of zone identity, right? To create an identity per zone. What Spiffy does is workload identity, right? An identity per workload. It's actually even better than an identity per zone. Because the zone is more like a node, right? So you can do even more fine-grained. We need support for distributed systems. Spiffy is designed to have a uniform control plane. So no matter where your applications are running at all these different platforms, they have this kind of unified way to talk about identity in all of these different places. We want no secrets. Spiffy has a zero trust model. That's the whole idea, right? You can start knowing nothing, and you can kind of figure out properties about different workloads and use that to assign these identities to them. And finally, we want that hypervisor-rooted trust. And Spiffy, of course, doesn't have this directly, right? They don't assume a hypervisor, but they have a lot of different methods for testing workloads, and it's a very pluggable architecture. And so we'll get more into that in a minute, but this all kind of starts to fit together. So I mentioned this Spiffy thing, so I'm going to step back again and say, what even is this? So Spiffy, or Secure Protection Identity Framework for Everyone, is basically a framework that does all these things I just talked about. It's a framework for workload identity. There's a few different components of it. There's more than this. This is the stuff you have to understand for here. The big thing is a Spiffy ID. This is the identifier that's assigned to the workload to kind of identify it. It's formatted like this, Spiffy : / the name of your trust domain. This could be kind of any string / the workload identifier. So the trust domain is kind of the name of your root of trust. It's kind of your namespace, sort of. And then the workload identifier is usually associated with some properties of the workload. So what folks will often do is use the workload identifier to say like, what namespace is something running in or something else like that. And you can kind of use this verification process to kind of prove those properties before then assigning an SVID, or a SPIFFE verifiable identity document. The SVID is basically a signed version of the SPIFFE ID in either an X509 or JWT format. And so it has the SPIFFE ID, it has signature information that kind of allows you to link back to the root of trust in a way that works a lot like Web PKI for folks who are familiar with X509 from that context. And this also helps you tie a cryptographic ID, cryptographic key, right, to this whole identity. The way you get these identities associated with a workload is kind of a two-step process. You first do node attestation so that the root of trust kind of establishes trust in your node, and then inside of that node you do workload attestation for the particular workload. And we're going to talk more about that. But first we're going to talk about Spire, which is an open source implementation of SPIFFE. The SPIFFE spec, these are both actually CNCF projects, so kind of sort of a joint project, but separately listed. Spire stands for the SPIFFE runtime environment. It's basically just an implementation of the spec that includes a Spire server that acts as kind of that root of trust, your signing authority. It manages the keys. It kind of helps. And anytime you want to assign a workload, you kind of register it first with the server. And the Spire agent runs in each node. So we talked about that node attestation, workload attestation. The Spire agent is kind of the machine inside the node that does all of that work. One of the things the Spire agent does is it exposes a workload API that workloads can use when they want to request an SVID. They ask the workload API, and then the agent kind of does all this work and then gives it to them or not. So very quickly, I'm going to go over node attestation. So there's a lot of details missing here, obviously, but the big idea is that when you have a node that wants to do node attestation, it requests some information from the underlying platform. This is an intentionally vague term. It can mean anything from your cloud provider to like a TPM on the machine. Anything like that can kind of establish where the node is running, if it's running kind of where you expect it. The agent then sends that information to the Spire server, which then verifies back with the underlying platform. And then if everything works out, it issues the SVID to the node and kind of gives it permission to be a node kind of in this network. And then what that node is able to do is attest to workloads. So the workload, kind of a similar process, it requests an SVID from the agent asks a local authority. In this case, this might be like your kubelet if you're running in Kubernetes. This might be features of the operating system itself that the workload is running on that can kind of say, what is the process ID? What is the namespace? What is, is this running where you expect it to be running? What are the properties of it? And then the agent can actually use that information to request from the server an associated SVID, right, that has those properties, and then assigns that to the workload. The benefits here, besides what we already talked about, is we have zero trust, right? So you don't have the workload here doesn't have to be preloaded with anything at all, and it can still be assigned an SVID with this process. And some of the things I didn't quite explain in detail is this also has short-lived identities, and which means that you can have automated rotation, right? You don't have long-lived secrets lying around that could be compromised. Everything kind of comes with built-in rotation as is. And because it's an open source spec that's been around for a long time, it's very platform agnostic and compatible with a lot of existing systems. So what we're going to do with this is we're going to try and use it with Adara to get cryptographic proof that a workload is actually running in a zone. To do this, we're going to kind of create a modification to node attestation with the hypervisor as the underlying platform, right? Instead of using a cloud provider, we can kind of do this all through the hypervisor instead. We're going to do workload attestation with the existing Unix selector. We're running these workloads basically in an operating system, so we can just use that existing stuff, not reinvent the wheel. Because we have these isolated zones, we're going to keep key material in one of them. So one of the things that the server piece of Spire has to do is manage keys. And one thing they suggest doing to kind of harden it is kind of keep a separate key database somewhere. And we're like, well, if we're going to keep a separate key database, let's put it in a zone, make it very isolated and hardened. And altogether, this will get us all the benefits of SPIFFE, compatibility with all of this other work, but we get this hypervisor back to trust. So here it is in diagram form. I'm going to break this down, don't worry. So start with some initial setup. So you have that key manager zone I talked about. That has all the keys for the system. The initial version of the server is self-signed, right? And then you can use, then once that's established, it can rotate from those keys. So those private keys sign the SPIFFE bundle, which ends up in the Spire zone. And then the Spire zone, that SPIFFE bundle needs to get to the agent to kind of initially provision that trust. And I'll show you how we do that in our system in particular. I think often what happens is this is can be a manual configuration step, but we had a cool workaround there. Then we have node attestation. But we used what's called a join token in Spire, and, rather than doing a custom node attester. And I'll talk a bit about the trade-offs with that choice later. But basically what the join token is it's a one-time use token generated on the server that can then be used to do workload attestation. And this is really designed for kind of manual configuration, but it worked really well for us to be able to just copy that one join token through the hypervisor if they're running on the same system, and you can get this kind of guarantee that it's hypervisor mediated, so it only works if they have access and are actually running in a micro VM on that hypervisor. But anyway, yeah, so you get the join token to the agent. The agent then sends that with some other configuration information to the server, which if everything checks out, issues an SVID to the node. And then inside the node, you can do this existing workload attestation process. Less detail here, because this is just the existing Unix selector that kind of asks some information from the operating system to do that attestation. And then finally, we have verification. Despite how complicated the whole diagram looked, the verification piece is actually very straightforward. All you need is the SPIFFE bundle and the SVID. And with those two pieces of information, you can kind of verify the chain of certificates and know that this particular identity is securely tied to this workload. So that's kind of what all the rest of this complexity is for, is to make this verification really straightforward. So demo time. Hopefully we're doing this live on a remote machine, so hopefully oh no, this is what I was hoping wouldn't happen. We have a broken pipe, 1 second. Unfortunately, because because it's running on a hypervisor, I have to be doing, I have that installed on a remote machine, which I'm trying to SSH back into right now. We'll give this like 2 minutes, and then I'll skip the demo and just explain what it would have done. You can find me after, and I can prove that it works. Yeah, this appears to not be connecting to my remote machine. So anyway, okay. Moving on. If we have time at the end, I'll come back and try and do that. Now I'm going to explain it in words instead. So what we were going to do is we were going to set up a zone that runs a Spire server. That's its own isolated zone. And so that sets up the configuration. This part's pretty straightforward, just kind of using the existing Spire work in the zone. And then we're going to do node attestation through the hypervisor. So what we're going to do is we're going to spin up a zone with like the flag with Spire. And what that's going to do is it's going to request through the hypervisor that join token from the server. It's going to use that join token to set up some configuration and then send that configuration to the Spire server. Sorry, this would be better with the demo, but we're just explaining it. Oh, there's nothing there. Sorry. We're doing it really just with words. Okay, here we are. And then, that does the node attestation through the hypervisor, and it kind of establishes trust in the node. And then what we do is we do workload attestation, where we register with the Spire server a workload with some particular properties, and then when we call the workload API, it's able to kind of get that SVID from the client. So hopefully that made some sense even without the demo. And then with this whole thing, this is compatible with other SPIFFE identities and verifiers. What can we build with this? So what you didn't see is that we have cryptographic keys tied to a zone. So with these keys, what we can do is signing and encryption. So the first use case is that one I was talking about earlier, that idea of remote attestation, where you can prove where your workload is running before it runs. The other one is mutual TLS. So when you have this key tied to the zone, what you can do is you can encrypt all traffic to any other zone, or really any other workload that has a key. And so you can encrypt that traffic between those two such that nothing, including the hypervisor, including the operating system, can actually read that traffic unless they have access to that key. So this is really cool, and this can help you protect against a lot of different attacks on things that are able to read traffic, right? Because it's all encrypted. So even if you read it, even if you can read it, you can't actually see what's going on. And then finally, a kind of fun use case around sign build provenance, if you kind of use this with a secure build environment. And I have a whole diagram for that, don't worry. So the first one that I want to dig into a little bit is this idea of remote attestation. This is kind of a simplified version of the RATS architecture. If you want to read more about it, that's what this is based on. And the idea is that you have a verifier that has access to kind of some reference system state. And there's all these kind of clever techniques that they use to kind of hash the system state on a zone, or basically in an operating system, where it tells you what's going on basically in the system, and then it hashes that. You can sign that with the SVID, and then send it to a verifier. And if they know what that state should look like, they can know that it's in a good state before sending any sensitive data into the zone, right? So this is better than just having the key and knowing, hey, we got this key through the hypervisor. This is like, no, this was provably where this is actually running. And of course, the SVID is verified with that SPIFFE bundle, so you also have that kind of chain through the root of trust. The other kind of cool use case here is this idea of non-falsifiable build provenance. So this is one of the requirements for SALSA level 3. SALSA is the secure levels for software artifacts, I think. It's a standard that does that kind of provides these levels for how to get different pieces of software supply chain security. We're focused here on the kind of build track, is what they call it in SALSA. And the way they kind of look at it in SALSA is in order to do a build, you have this build controller, takes in some external parameters, and then it directs different build tasks, where each build task does like one little piece of the build, and then the build controller kind of puts that together and then sends the final result back to the system. So what SALSA requires is a couple of different things. It requires the tasks to be isolated. This is one of the things we get with micro VMs by default, right? They have really strong isolation. They want provenance information. What this is signed information about what happened at each build step. So basically for each build task, you take the input, the output, and what you did, put that into a format, sign it, and then at the end, they kind of put that all together and give it to someone at the end. For the big thing this gets you is that if anything goes wrong, at the very end, you can tell exactly where it went wrong, right? So it's really easy to track down a compromise. But for SALSA level 3, one of the things they want is non-falsifiable build provenance, which means that each build task needs a unique key such that signatures can't be forged by the controller. Because if the signatures can be forged by the controller, that means that you don't actually know where it went wrong, right? You just know that something in the build process signed something wrong, which is not quite as useful. And so the reason we get this with SPIFFE is that we have these unique keys associated with each zone. So if we have the build controller in one place and each of our build tasks in a separate zone, they each have individual keys associated with them. So you can kind of get this verification of the whole thing. So as you can see here, you have the build controller. It assigns the task to the build task zone, which creates this SALSA attestation. That's that provenance format. It's very related to the in-toto attestation format as well. If you're looking into this, I recommend looking into that as well. The build controller collects this into the whole SALSA provenance format and sends that to the verifier, who's able to kind of verify that every single step of the build happened as expected. And critically, you can even say, okay, yeah, the input of this step, the output of this step matches the input of the next step, right? No one was like weirdly doing stuff in between the steps. So this can get you some really powerful kind of information about what's happening at every stage. And because it's properly isolated and because each thing has its own key that's uniquely assigned to that zone, this is all kind of cryptographically verifiable. So now I have a few lessons from configuring Spire, and then I'll try once again really quickly to get that demo running, and then see if we have time for questions. So first I want to chat a bit about how great the existing Spire tooling is, basically. It says pros and cons on the slide. There are some cons, but mostly pros. I was able to basically use the out-of-the-box GHCR images for the demo that you didn't see, and those are basically, the Spire server just works like that, and because of the way the attestations are so pluggable, I was able to do all the customization I needed to do without kind of affecting the core library, which is very, very cool. There's also some Helm configs for Spire that I've gotten running. I didn't use those for this demo just because I think the layer of Kubernetes added some complexity that makes it harder to kind of see what's happening, especially as we go all the way down to the hypervisor and then back up to Kubernetes. The one kind of con I would say is the client tooling. The way they kind of designed the Spire tooling is that you need to install the client, when you install it, has a way to call back into the workload API. But if you want to just access the workload API without installing the whole Spire client, there's not a super easy way to do that. It's not that hard to write, but that's maybe a space for improvement. The client provisioning, the kind of thing to be aware of here, that's kind of less obvious from the demo because I did it in the background, is that you need to make sure that you have access to the Spiffy bundle in that client in order to do any verification, in order to do this initial provisioning. And you need to kind of set some configuration information. So even if you install these GHDR images, you have to make sure that you're setting the configuration you want, picking which attesters you want to be using, making sure that all matches. So it can be a little finicky, but it's pretty straightforward format, pretty well documented. And then, yeah, I want to talk a bit about that join token kind of design decision. The join, I think it works just fine for setting this up, and it's through the hypervisor. The downside is that it's a single-use token, which is incredibly annoying for debugging because if any one thing goes wrong, you have to make sure to reissue the token for the workload, even if it's the same workload, kind of over and over again if you're debugging. And so I think in the future, there's definitely space for this to have a custom node attester. There's a format in Spire even for making these where you make your own custom attester, kind of register it with Spire, and then you can use it. That might be a better way to go here in the long term. And yet, not much to say about the workload attestation. The existing support for Unix worked great, so that was awesome. All right, thank you. And we're gonna, here, we can just do questions. I can try the demo later. Thank you all. I'm gonna try this really fast.
So this idea that you're using the hypervisor to attest things, it reminds me a little bit of some of the work that Matthew Garrett was doing when we were both back at CoreOS. He was working on what we were calling distributed trusted computing, and it was the same kind of thing. It was, the idea was the TPM verifies the bootloader verifies the kernel verifies things on top of the kernel, up to the idea was you could take a Kubernetes cluster and stick it in a hostile environment, and either it would run correctly or it would simply not run. Were you aware of that work when you started on this, or have you looked that up as you were working on this?
Yeah, no, this was definitely not done in isolation. I think this whole idea of secure boot, of again, confidential computing was one of my big inspirations when I was looking at this in the first place. Yeah, this idea of chaining that trust is, yeah, it's definitely, I didn't come up with that myself, right? I'm just kind of using it in a new way. That was my whole idea here, is that you can use it in this new context. So.
Any more questions? Nope. Okay. Thank you very much.
Thank you.
Now we have a short break, and we'll be back at 4 o'clock. Have fun.
are for core functionalities, and also the region specific.
Guys, please have a seat. Yeah. All right, we are ready to start our next session. We have Yash, and we should supposed to have Niklit as well, but he didn't make it to come, so he'll be virtually recorded and played on stage. So they're going to talk about managing storage at scale at DigitalOcean. Take it away.
Thank you. Let me just come over the stage. Thank you everyone for staying for my talk. And this is my first time coming to Atlanta, and first time attending KubeCon NA as well in the few days as well. So I'm pretty excited, and that's a great start from the Cloud Native Rejekts. So in today's session, I'll try to share how we manage our storage platform and how we use Argo CD in our storage platform at such a scale. So the title was like managing millions of storage volumes at at scale. Now, to manage the storage volumes, there are a lot of other things also plays role in the technology. One of them is Argo CD. Argo CD is adopted by DigitalOcean at very large scale, not only in the storage team, but also adopted by various other teams which manage different parts of the DigitalOcean services. Now, let's start with my introduction and my co-speaker introduction. I'm Yash. I work at DigitalOcean as a developer advocate. I'm also a maintainer of a project called Mishri. Mishri is a CNCF Sandbox project. It's a cloud native manager, helps you to manage and design your cloud native reference architecture, which you can check out as well. My co-speaker, Nikhil, he worked as a platform engineer, senior platform engineer at Storage Team. And he helped me put out this story when I was discussing with him, I think 4 months ago. I had a discussion with him about the Argo CD, and he mentioned how we are using Argo CD throughout our storage platform. So he is not able to make it today, and he is sorry about that as well. However, he recorded a short video for you all guys, and he will also, and I will play that part, and he will share how we are doing it with Argo CD. So let's move forward. Let's try to understand what are the offerings that DigitalOcean provide in the storage space. We provide both the object storage and the volume storage, and spaces and the volume storage. And these are the services like, I think, the S3 compatible services and the network-based block services, which DigitalOcean provide. Now, this is very common. Now we understand, okay, what are the services that DigitalOcean provide. Now let's try to understand at what scale I'm trying to talk about. DigitalOcean manages more than 240,000 block storage, thousands of object storage. I reached out to object storage team to get out the actual number, but I was not able to get it before the time of the talk, so I put it 1,000 because I know that the storage, the object storage which we manage is 3x the time of the volume storage. So it is also very high number. Now we have 13 plus clusters across 11 plus regions. So these are all our customers are able to run and create these object storage globally throughout the So on every region and every data center, we have a specific cluster which helps host these services. Now, applications managed by Argo CD. So Argo CD helps us manage the core functionalities like CNSI and CSI, CNI security policies and everything. So on Argo help us roll out and install these services throughout all of the clusters. Also region-specific applications. So in region-specific, sometimes we have to follow the government rules or there are any specific customer requirements. So those are also Argo CD helps us with. And one of the talk main highlight was we adopted a centralized management. I will share with you, Nikhil will share with you how that is happening and why we went with the centralized management where we have a single Argo CD manager, which is controller, which is helping us doing rollouts for all of the clusters. So let's try to understand the architecture. And I'll call Nikhil to explain this architecture. And let me try to play the video. So I have to maybe probably reshare. So just give me a second. Okay, if I do reshare. I think I can play the video.
Hello, everyone. My apologies for not being able to attend this wonderful event in person, but I'm thrilled to join virtually. In the following slides, I'll guide you through the architecture of the Argo CD setup, which is managed by the storage engineering team at DigitalOcean. The system involves multiple Kubernetes clusters in different regions for storage services with a dedicated controller, or also called local Kubernetes cluster, managing their lifecycle. Argo CD takes care for deploying both global applications, which are for core functionalities like CSI, CNI, and security policies, and also the region-specific applications. All applications are centrally managed by a single Argo CD cluster running on the controller Kubernetes cluster, which is also called the local Kubernetes cluster. A closer look at the image reveals that the local Kubernetes cluster hosts all the Argo CD cluster-related CRDs. Also, these clusters have applications required for maintaining the security compliance and the control plane functionalities. The downstream clusters only have CRDs deployed in order to support blue, green, or canary deployment strategies. These are the clusters doing the actual heavy lifting and hosting region-specific storage services. Now, managing deployments across multiple Kubernetes clusters is difficult due to the need for distinct manifests, manual updates, and repetitive configurations. Application Set, an Argo CD feature, solves this by automating the generation and management of multiple Argo CD applications from a single template. This process involves a generator creating parameter sets for each target, a template rendering with each set, and automatic application creation and updates. This approach offers several benefits, including adherence to the DRY or do not repeat yourself principle, enabling you to write once and deploy everywhere, along with consistent configuration, automated setup for new cluster, and enhanced maintainability through single file updates. Our storage services utilize a shared platform with permissions and policies managed through Argo CD projects. This platform is used by multiple storage solution offerings like block storage and object storage. We assign these permissions using OIDC groups. Argo CD projects, that is also called app project, facilitates this by providing a logical grouping mechanism that enables multi-tenancy and access control for applications within Argo CD. The Argo CD project feature offers several key benefits, including multi-tenancy for multiple teams, enhanced security to prevent unauthorized deployments, compliance with organizational policies, and finally, the governance over the resource usage per team. Argo Rollouts manages application deployment strategies in our Kubernetes cluster. It offers advanced patterns like canary and blue-green deployments. Now, canary deployment involves gradually shifting traffic to a new version, monitoring metrics, and automatically rolling back if issues arise. Blue-green, on the other hand, run both versions simultaneously, allowing testing of the new version with a preview service and offering instant cutover with quick rollback capabilities. Now, Argo Rollouts uses a rollout resource to replace standard Kubernetes deployments, enabling progressive delivery. It also utilizes an analysis template to define success metrics using data from sources like Prometheus, which helps automate decisions during rollouts. Additionally, Argo Rollout supports robust traffic management and allows the manual approvals, providing greater control over deployments. Now, I would like to call Yash to present you with the upcoming slides.
Awesome. Thank you, Nikhil. Let me reshare the video. Oops. Let me reshare the window. Okay, let's just a second. Oops. How do I reshare it? Okay, I can play it, I think, from here itself. Okay. I hope this works. Awesome. So I hope you get the idea how we are using Argo CD in our storage platform. Now, the architecture was quite simple. It's not like pretty complex. We are doing pretty heavy thing with Argo CD for our storage platform. You can see that like we had a single Argo CD cluster controller installed in our managed controller Kubernetes cluster, which we call a local cluster, and it manages all the downstream clusters for which does actual heavy lifting or install or provide the services for the storage platform. So it's just a simple template I just added because this is something similar to like we follow at DigitalOcean. It's not quite exact what we do, but it's quite similar at how we follow it. And it's also a very simple generic one. So let's move forward. It's like the Argo CD managing Argo CD. Okay, so my Argo CD is also doing a range. We have a rancher sync with Argo CD as well to make sure if there is a new cluster installed, we are able to automatically add it in our Argo CD generation Kubernetes list. So once the Kubernetes cluster is their new Kubernetes cluster is there, it has a rancher sync. Now there is less information right now in this talk about the rancher Argo CD sync, but we have a blog out which I will share with you, which is more detailed about the Argo CD and how we are doing with the rancher sync, because it will take another much time to explain that particular part. Now the IAC management, Argo CD deploy. Yeah, so Argo CD's deployment itself goes through Ansible. So at DigitalOcean, our Argo CD's deployment goes to Ansible. If there is any upgrade or rollout going through for the Argo CD itself, goes through the Ansible playbooks. Now, what is the impact of it? Impact is like it helps maintain all of our storage platform, which are millions of storage platforms we manage, instances we manage each year, every month. And it also helps maintain the compliances all over the global regions and reduce the deployment complexity for our engineers and the team which actually manage the Storecases platform. Now, Storecases platform, it's an internal platform that DigitalOcean uses. It also connects with DigitalOcean Argo CD to help with the rollout. What is Storecases? Storecases help us manage the deployment of our internal instances that we have. So yeah, so one thing that I just wanted to add is like, I think when I was working with Nikhil to put out this story as a talk, I literally find out that we are working at such a large scale. We are managing our clusters globally and managing such level of storage. I figured out the architecture was quite simple. And I was able to understand the architecture within few minutes, I think. In just a meeting, I was able to understand what's going on within the whole team. And it's not always that easy, trust me. I was working with DigitalOcean's Kubernetes team to put out the story for different talk. And that was quite complex because they managed 20,000 plus clusters to run the Kubernetes that we provide Kubernetes services. But when I was working with the storage team, I figured out we are also working at such large scale, but with quite a simplicity. It doesn't require a complex thing. So I was like, sometimes we always don't need a complex architecture to manage at such a scale. It's always the business output that we want, and are we able to do it with the simple architecture, which is also scalable? Is this it? Yes, quite honestly, this is it. And this is how we manage our storage platform. Why? Because at DigitalOcean, from the team, from the engineering team, what I heard is like they usually follow scaling with simplicity. They try to be as simple as possible, try to avoid unnecessary things which doesn't require and doesn't provide the business output for our customers. For the home tech resources, this whole story is more complex, little bit, which is also written by Nikhil as a blog. So if you are interested in how we are doing it more internally, how we are doing with the rancher sync, how DigitalOcean's Argo CD connects with Storecases platform, which is DigitalOcean's internal platform. Nikhil wrote a detailed blog on that, which you can check out as well. Thank you, everyone. It was quick, but yeah, this was the whole talk. Thank you, everyone. I'm up for Q&A. If you have any questions, I would love to take the questions.
We have time. Okay.
I think I missed it, but how many Argo apps is the biggest Argo CD instance has?
DigitalOceans have the one Argo CD single cluster installed in a single cluster, and it manages all the downstream clusters. So it's a single Argo CD cluster. Yeah.
But how many Argo apps are in total?
That I don't have information on. Quite the exact number, I don't have information, which I didn't got from the team. But I can connect with you, and if you need more information, I can connect with you, the engineers.
Anyone else? We have time for questions. Nope. Thank you very much.
Okay, thank you.
Thank you.
Thank you, everyone.
All right. right, the next one will be at 4:35, so we have some time for coffee and recharge. I think we can start, right? Okay, hi everyone. Welcome to the last session, a regular session for today. That's Caleb, and he's gonna talk about WebAssembly. Last time I introduced him and he was like super pumped, and I hope you can do the same, right?
I'll bring it, I'll bring it. Great, I'm so excited to be here. Like he said, this is my second Rejekts conference, second time I've got to speak here, so it's wonderful to be back. Today we're gonna be talking about truly portable code, serverless WebAssembly in a distributed world. First, a little bit more about me. My name's Caleb Shep. I've been a software engineer at Fermyon for about 3 years now. I do some work on our closed source stuff and a bunch of work in the open source on our project Spin and trying to bring open telemetry into WebAssembly. I just flew in from Canada yesterday. It was snowing, so it's kind of a nice vacation for me to be here for a week, although I've heard it's going to get a bit colder, so we'll see what happens with that. Let's dive in right away, though. I got a lot to talk about today. So we're going to be learning about WebAssembly today. We're going to be talking a little bit about Spin, the open source project to make using WebAssembly easier. Then we're going to be deploying that application to a few different places, Spin, Cube, and Fermyon WASM functions. And there's going to be a lot of demos today, a lot of hands-on code. Awesome. Okay, so starting at the basics, let's do a show of hands. Who's heard of WebAssembly here? Okay, everybody's heard of WebAssembly. We've done our work. So we all know here that WebAssembly can be contracted to WASM. Don't get confused when I keep going on about WASM. And I'm sure you've probably seen this super long and kind of confusing definition of what WebAssembly is, but I like to think about it more simply. So WebAssembly is just a compilation target. It's just another bytecode format, just like you would take a Java program and compile it to Java bytecode and then run that anywhere you can run a JVM. You're doing the same thing with WebAssembly. You have a program, you use your programming language's toolchain to compile that down to a WebAssembly bytecode, and then you run that WASM on a WASM runtime anywhere you can do that. Now, there's a couple implications of this. One of them is that your language needs to add support to its toolchain for compiling to WebAssembly. We've seen great strides in the community of this improving over the past few years. And then the second implication is you need a runtime to run this somewhere. So you might be familiar with things like SpiderMonkey or V8. These are the JavaScript JITting runtimes in the browsers that also have the ability to run WebAssembly. But there's also WASMtime, which is kind of the marquee runtime for WebAssembly on the server side. So why am I so excited? We were just talking about the WebAssembly hype train and how all the WebAssembly people are so excited about it. Why am I so excited about WebAssembly? The reason is because it turns out that us server-side engineers, building serverless products, care about all the same things that browser engineers care about. We care about having security because we're running arbitrary code and we want that to be sandboxed using the sandboxing we get out of WebAssembly and capabilities-based security. We care about performance. Not just near native execution speed, that's just kind of table stakes to enter into the game. But importantly, we care about no cold starts, right? Because in traditional serverless, you're paying the penalty the first time a request comes in to start up like a Firecracker VM or something like that. And so there's a cold start on the initial request. And WebAssembly allows us to avoid that because it has sub-millisecond instantiation time for instances. We care about it being polyglot. We want support across all the different languages that you might be using. And then, of course, we need portability. You want to be able to run it on all the different permutations of architectures and platforms and such. So, WebAssembly is giving us all this property that's wonderful. And so we're going to tie that in with Spin and see how we're using that. But as you can maybe tell, I'm really passionate about WebAssembly. So I want to stop for a brief second and give you guys kind of hints into two things that you probably heard about around WebAssembly. We don't have time to fully unpack them today, but they're very exciting. The first thing is the WebAssembly component model. And so, kind of the textbook definition is it's a broad-reaching architecture for interoperable WebAssembly libraries and applications. So really all it's saying is you take like a WebAssembly module and you can wrap it up with explicit imports and exports, an interface. And then you can use these to compose them together with other WebAssembly components. And then you can compose that further and wrap that in another component. And this has a ton of really nice properties about changing how we can write software. There's a little bit too much to go into there, but Luke Wagner, one of the creator of WebAssembly, has described a component in this like very wordy phrase I like, but it calls back to all the things that WebAssembly offers, where components are standardized and they're lightweight, right? They have no cold start. They're secure and sandboxed and polyglot, cross-language. So yeah, keep your eye open for the component model. It's changing a lot of things ways that software can be done. Second thing worth noting is WASI, which if you haven't heard of it, stands for the WebAssembly System Interface, or I've heard a better name, or how you should think about it, is the WebAssembly standard interfaces. And it's really just taking the component model, which is this definition of how all these components are communicating with each other, and then it's defining a set of standards on top of it, saying we're all agreeing this is how we're going to read environment variables, or this is how we're going to read files from the file system, things like that. Okay, so we've laid a baseline for WebAssembly. What is Spin? Spin is the framework for building and developing and running these event-driven serverless applications. It's really meant to kind of take you through the entire life cycle of using WebAssembly for this. So it's going to start with you've got nothing and you want to scaffold out a new application, you want that templated. It's going to walk you through actually developing that application and using SDKs to access different resources like key value we'll see in this talk. It's going to allow you to run that locally. Even before running locally, it's going to allow you to build the application and compile it to WebAssembly and allow you to not deal with a lot of the complexity that exists in the WebAssembly ecosystem, but just run spin build, a super easy command. It's going to let you run that locally. It's using WASM time under the hood for that, and then it also ties up and makes the deployment process really easy. Okay, so I'm a really big fan of like motivation and use cases, and I also, totally honest, just wanted to spend some time generating art with ChatGPT on work hours. So I'm going to be pretending today that we've been hired by totally not fake Marketing Co. And we're a new software engineer, and this company does digital ad campaigns for people, and they have a need for branded links. So they want to create a URL shortener, so you can take your long, tracking URL that's kind of gross, and you can show them a branded URL. So it's our first day there, and we're looking to build a URL shortener. This thing needs to be fast, it needs to be secure. We want to be able to easily run it locally and test it, but do that in the same way that you might do something with how you deploy it. So let's dive in to a little demo here and start exploring around with this. So first things first, let's just like explore around with Spin. So I've got Spin installed here, and I did a quick check, but this is good for size for people. Cool, general nodding. So the first command we're going to care about here is spin new. So spin new is going to allow us to template out a new application. You can see here a big list of all the different kind of trigger types. We support like Redis and HTTP and a bunch of different languages. I'm a really big fan of Rust, so we're going to be building an application in Rust today. So I can go ahead and run that, and we'll just create a little hello world application here, and we'll give it a description, my rejects app. Cool. And then we can just go ahead into hello world. And we'll see a couple things in here. We're going to see a cargo.toml, because this is just like a normal Rust project. And we're going to see a spin.toml. Now, the spin.toml, we also call it the application manifest. This is like the kind of base description of what's going on in a spin application and how that works. Right at the top here, you've got application, just kind of a bunch of boring metadata. What's the name of this application? What's a human readable description? Those kinds of things. But really, the beating heart of an application manifest is you've got components and you've got triggers. So we'll start with the trigger. The most common trigger you're going to encounter in a spin application is the HTTP trigger, right? A request comes in, you want to serve that request and return a response. So we're saying here, anything coming in on any route it to this component. Oh, hello, W world. And so, but you could imagine, you could have like a Redis trigger, messages coming in on a Redis channel, or a Kafka trigger, or, trigger for anything kind of event-driven. Then we also have the component. So the component is nothing more than just a WebAssembly component, right? So we're pointing to the source. Somewhere on disk, we've got a WASM component living, and we'll go take a peek at that. And then we've also got this build command, which is wrapping up how we do the compilation of this Rust code, in this case, to WebAssembly, which is nice because we don't have to deal with all the annoying incantations you might have to know. Let's take a look at the source code for this application too. So it's really simple. We got one function here. We're using a little Rust macro to declare when this WebAssembly component's executed, go ahead and execute this function, and then we're just printing a log statement and returning a 200. So if we go ahead and run spin build, that's going to go and build the application for us, and we will patiently wait for Rust compile times. In the meantime, I'll just pre-type out, we're going to curl this app here, get that ready. Great, so we've got it built, and actually I just want to show that. Okay, that's fine, because I put a W in there. Right, so this is just a WASM file on disk, and I'm just using WASM tools to dump it out. The whole point is you don't need to think about the WebAssembly and really know what's going on in there, but I just want to kind of show that, that we've got this just WebAssembly component living there. And then if we run spin up, we go ahead and have that running locally using WASM time, and we can curl the application. We'll see hello world. We can see we're getting a 200 response back from that curl, and we get some log statements out the other side. So that's a really kind of simple demo of what spin looks like. But let's go back to this motivation. We're working for this company. We want to build this application. So I'm actually going to just go to a pre-written version of this because we don't have time to write it here today. And we'll go look at this application. Okay, so first things first, let's talk about like what we're building and the functionality we want here. We're going to be building just a really simple URL shortener. So a GET request comes into some sort of endpoint with like a slug. Maybe it's like Wikipedia.org is doing an advertising thing and they want smart to redirect to wikipedia.org. So you take that slug, and if the mapping is stored in the back, then you just return a 302 to redirect it. And if it's not found, return a 404. We also need the ability to configure these mappings, so we'll just have a simple endpoint where you can post to with a body containing the URL, and then we'll return a 201 when that's successfully created. In any other case, go ahead and return a 404. I'll have a link to this at the end. It's worth noting this was originally a full workshop, so if this is interesting to you, there's materials for you to follow along and build all these things yourself. Okay, so we're doing this URL redirecting, and we're storing these mappings, but we need to store them somewhere. And so thankfully, Spin comes with a key value store out of the box that you can just easily use. And so why does that matter? That matters because we can't just store it in the memory of this process, right? I mean, it matters for obvious durability and like production reasons, but separate from that, every single time this component's being executed, the instance is being spun up, this code is executed, and then the instance is being taken down. So there's no like, oh, I can just stick it in a global variable in a hash map or something and store it between that. It's a completely separate like instance every time a request comes in. So we need a place to store it. So we'll go ahead and stick it in a key value store. And to do that, we need to edit the spin.toml, and we need to say, hey, by the way, this component has specific access to a default key value store. This is coming back to the capabilities-based security. The component should only ever have access to things you explicitly say that it should have access to. Great, so we've got this key value store, and we've given access to it. And then, the logic for this is pretty simple. So we've still got the same handle function. We're using a little simple HTTP router here, saying, when there's a GET request, call the redirect function, and when a POST request, call the shorten function. When we redirect, we just pull the slug right out of that URL parameter. We go ahead and use a Spin SDK to open up that default key value store. Then this is some just nice Rust syntax to say, hey, if you go look in that key value store and you find something, go ahead and return a 302 redirect and print a log statement that we did it. Otherwise, if you didn't find that thing, go ahead and return a 404. Same thing with shorten here. We're pulling the slug out of the URL parameters. We're pulling that URL out of the body, and then we're shoving these things into the key value store and printing that out and returning the 201. It's worth noting that locally, the key value store for Spin is, Cloud Code, is backed by SQLite. So there's just like a local SQLite instance database on disk. Okay, so if we just go ahead and build this guy. Perfect, I've already got it built. And then we can run up spin up. And actually, fun fact, you can do spin up -- build, because I always forget to build things when I change the code. And then let's just go ahead and curl this guy a little bit. So we'll go curl localhost. Let's say smart is going to be redirected to wikipedia.org. And -i, so we can see the status code there. Cool, so we've created that mapping. Then if we go ahead and just curl this, we'll see we get a 302 redirect off to wikipedia.org. We could, for fun, just do a little -l follow and get all the HTML for wikipedia.org. Perfect. So that's the URL shortener application. Let's go ahead and keep going through the slides here. So we've written this application and we've shown to some of our coworkers, and it's a smashing success. They're all super happy. with how it's working. But everything runs on Kubernetes these days, and so totally not fake Marketing Co. has a Kubernetes cluster running somewhere that we need to deploy this into, and so how are we going to do that? The answer comes in SpinCube. So SpinCube is the project that kind of streamlines the process of running spin apps inside of a Kubernetes cluster. Now, SpinCube itself is not a monolithic project. It's actually a collection of a number of sub-projects that we've worked on with, in tandem with a bunch of other companies. Kind of the two core parts of it, as I like to think about it, is there's the spin operator, which is a Kubernetes controller with some custom resources and custom resource definitions that we'll take a peek at. And then there is the container dshim, which is like the actual kind of guts of how are we running WebAssembly workloads on Kubernetes. Unfortunately, we don't have time to super dig into that today, but we'll see a little bit of how that works. So, right, we've got this custom resource definition for a spin app that we want to apply to our cluster. So you're going to write a manifest, and you're going to apply that manifest to the cluster. This spin operator controller is going to be watching for that custom resource, and then when it sees it, it's going to reconcile and create a deployment and a service backing that. And then this deployment is just some pods running your application. But what's actually going on under the hood is that these pods are using a special runtime class to actually use a container dshim and directly execute WebAssembly with spin instead of running a container. Perfect. So we'll dive back into the code here. I already have created a Azure Kubernetes Service cluster for us to kind of poke around and explore, and I've already installed the spin operator on it. So if we go, where'd it go? We can go look at the logs of this. We can see we've got a spin operator running here. It's watching for these custom resources. And we can go look at the CRDs. We can see I've got spin apps. So that's going to be the actual applications we're applying to the cluster. And then spin app executors, where in this case, we're just going to be using the container dshim spin executor, but there are other ways that they can execute, which is for a different talk. Just for a little demo, let's go ahead and get rid of that guy. Look through my history. There we go. Okay, so this is just kind of like a little hello world application that we can apply to the cluster. And so if we go look in spin apps, we would see we have this simple spin app running now. And then if we go look in the deployments, we should see that it's reconciled and it's creating a deployment for this simple spin app. If I go ahead and port forward this guy to port 8080, I can curl localhost 8080 hello, because it's a weird app, and we can see that that's working, right? So we're going through this port forward, we're hitting this pod that's using the container dshim and running spin and handling this incoming HTTP request and executing that. Great, so we've got kind of like a rough idea of what's going on with SpinCube here. Let's take our URL shortener and actually apply that to the cluster. So if I come here, I've got a manifest.yaml. Couple things going in here. So this is kind of just your standard custom resource. It's a kind spin app. We've called it URL shortener. And we're going to be referencing an image here. This is an OCI image of our application, which we'll need to push up. This OCI image of our application, it's purely just holding the WebAssembly for your application and the manifest. There's no other layers. There's no like operating system. You didn't accidentally pack curl unnecessarily into your image for your production application. And we'll see in a second how you can push that up. All the kind of other standard things you're used to in manifests, like if you're doing like a deployment, you can set replicas and image pull secrets and like all these different kinds of things. But then also we need to account for the fact that we are using a key value store. And so what's going to be backing that in Kubernetes? So I've actually installed a valkey, which is basically Redis, into our Kubernetes cluster, and we're using runtime config here to dynamically configure spin and say, hey, instead of using SQLite locally for your key value store, for the backing there, use Redis in this case. And so we're referencing a secret in the cluster to get the URL and piping and plumbing that through. So basically, we're just using Redis in the cluster. If we weren't to do this, and we had 3 pods running, each pod would have its own spin instance running and its own SQLite database associated with it. So they basically would not be coordinating the data there. But in this case, we're using the shared data here. So if we go ahead and spin build, make sure that's run, and then we can do a spin registry push. So this is just going to package up this application into that OCI image and push it into one of my favorite tools, ttl.sh, just an ephemeral registry, not authenticated. So if somebody were to push something to spin Rust right now, I'd have a really bad time because they could hack my little demo here. But we're hoping that's not going to happen. So we'll go ahead and apply the manifest.yaml here to the cluster. And then if we come back over to K9s here, we can go, let's look at spin apps first. We'll see that we've got a URL shortener application running now. We would see we have a deployment. Yeah, there we go. And we can see we've got the 3 replicas running. We can look, right, that's the kind of familiar spin output that we were used to. And then let's go to the service, just because we've got 3 pods running. Let's port forward this guy to 81. And we can just do a little demo. Is it in the history? No. Yeah, close enough. So we'll port forward that, and we'll send it to Smart. Cool, so we've got that created. And then let's just go ahead and curl that. Cool, we're getting the 302 back. Let's go peek into K9s again. See if we can get the logs for all these guys. Perfect, and we see some logs from that working there. Now, the important thing I want to note about SpinCube, well, is really 2 things. The first thing is you can basically just do all the normal Kubernetes stuff you're used to. You're just using pods and deployments and services here. The pods are running slightly differently, but wired up to all the things you're used to. Observability tooling, auto scaling, all the different kinds of things are just going to kind of work out of the box because we're using Kubernetes primitives here. Second thing I want to point out is we wrote the application once. So we have a spin application, and we ran it locally, and it was backed by a SQLite database locally for that key value store. Now we took that exact same application. We didn't even have to rebuild it. I did run spin build, but nothing actually changed. So we got the same artifact produced. Pushed this into a Kubernetes cluster. Now it's backed by a Redis key value store running a completely different compute scenario, but there's no changes to the application. And so there's like a full local dev match to what you're running in production, which is like really useful from a developer perspective. That's SpinCube. Just for the sake of time, because we don't have a ton of it, I'm just going to keep plowing ahead here. Let's go back to the presentation. Okay, so totally not fake. Marketing Co is doing amazing. You just shipped your app to production. These branded URLs are doing so good. We all know we love marketing, and it works so well. And so they've grown as a company, and now that's totally global. And so a real big problem for them is that they need to get these workloads closer to the customer because they're just running a single thing, maybe in a single region, and it's not close enough to the customer. What can they do? Well, this is where Fermion WASM Functions comes in. Fermion WASM Functions is a globally distributed PaaS running spin applications on the edge powered by Akamai's cloud. So basically, we're the orange dots in this diagram. That's where Fermion WASM Functions is running, and we're sped up actually by the blue dots. So anywhere there's a blue point of presence, we have fast backbone connections to. And so, right, you can imagine, if you have one data center running in the US, but you have a customer coming from Africa, they're gonna have a faster connection because we're gonna be closer. Now, the real benefit of this is we're decreasing the compute time through this spin WebAssembly technology, right? Because we don't have cold starts and a number of the other performance properties of WebAssembly. So we've shrunk that down, but if your network's still slow, it doesn't matter. And so thankfully, by distributing this globally, we're cutting down on both and really allowing customers to serve these things faster. So the exciting thing about this is it's the same workflow. You've got your same spin application, you've done the same local development workflow that you're used to, and you can go ahead and push it to Fermion WASM Functions. So let me just go ahead and show you what that looks like. Okay, so Spin actually has a capability of plugins. So you can see anything with a star here is actually a plugin. So there's like, you know, a JS to WASM plugin, which enables some things there, a bunch of different ones. But the one that matters for today, Spin Akka. And so normally I would run Spin Akka login. I'm already logged in, so I'm not going to bother going through that whole process, but that'll authenticate you into the cloud. And then it's really as simple as just running Spin Akka deploy. Yes, I think. Hopefully I cleaned up from my previous demo. I think I did. Perfect. So this is going to be deploying for us. Behind the scenes, it's doing the same thing of pushing that application into a registry. The same deal. It's just an OCI image with just the WebAssembly and the manifest. It's pushing that up behind the scenes. And then right now, it's distributing this out across all of the regions so that we can run throughout. I'll get these curl commands up here. Sub in the URL when this comes out. Perfect. Now, you know, on top of supporting the ability to deploy, we're also going to demo here that it supports logs, so streaming logs from all of these regional applications into a central place and streaming that. Things like cron jobs, a whole bunch of stuff. So we'll take the application here. Perfect. Let's do this. We would actually just expect that to 404 because we haven't defined that yet. But if we do this to -I, we'll see that we get a 201 created. And then if we just do a -I again, we should get that redirect. Moved temporarily, or we can just go ahead and open that in the browser, and we'll see that we get the redirect there. Let's go take a peek at the logs. We can do this. Sometimes they take a little while to propagate, and perfect. There we go. So we've got the application printing out those logs, and this is running globally here and resolving through the closest region. Yeah. I think the most kind of exciting thing about this is that, again, we can take the same application powered by WebAssembly and we can run it in a local environment in basically the same way that we can in Kubernetes or on the edge or all these different things. Right in the edge, we've got this global KV store that's like resolving, you know, globally distributed key value store, but you have Redis and Kubernetes. And so it's really powerful. This really kind of exciting developer workflow. Okay. That's pretty much all I have for today. Like I said, this is a workshop, so if you're excited by this, you can go ahead and scan that link and go through these things yourself or learn a little bit more about Fermio WASM functions. But thank you for your time, and I'll take a few questions.
Yeah, we have time for a few questions. Anyone?
If the application dies after the request is fulfilled, how does it remain listening on a port?
Fantastic question. So let's talk about the local scenario, and it basically works the same in the edge or Kubernetes. You have a single spin instance running, and let me not overload the term instance. You have a single spin application running, which is always listening on whatever event. So it's always listening for HTTP requests or Redis events or whatever. And then that, when it receives the request, will spin up the component for your application, run that, and then tear it down. So that the component that you wrote is being created and torn down, but the like actual thing listening and like executing your component is like always running.
Anyone else? Okay, thank you very much, Caleb.
Thank you, everybody.
We have a short break of 5 minutes, and then we do the lightning talks. I would like to ask all the presenters for the lightning talks to come up front, and Duffy is going to moderate that.
you guys hear me? Okay. So these are the talks that are going to be happening in the lightning talk round. Likely, it's going to be very much easier for you to use this microphone right here, the lavalier mic, or the mic that's on the podium, so we don't have to get mic'd up. It is a 5-minute talk. That means that at the end of your 5 minutes, there's going to be a big hook that comes from the right side of the stage and direct. No, I'm kidding. But I will give you a 3-minute warning and then a 1-minute warning, and then it will be time to call it. If people have questions about your talk, the hallway track out there in front will be the time to ask that question. Not in here, unfortunately, because it's going to be distracting from the next person who's giving a lightning talk. So if it's an important question, take it outside. I'm going to give you a 3-minute and a 1-minute. From the time you begin, I will give you a 3-minute talk. I will give you 3 minutes left and 1 minute left. Yes. Yeah, sorry. Yeah, exactly. After 2 minutes, I will give you the first warning, and you will have 3 minutes remaining. 3 minutes remain. 1 minute remains, and then the hook. All right. Exactly. 30 seconds. Any questions about lightning talks? File in, file in. I'm glad you're all here. I did, but I said that you couldn't ask questions about lightning talks. This is not one. 3 and, well, yeah, thank you, sir. 3 and 1 is good. Yeah. All right.
You know? No, I can just like this.
I can hold it to you.
I'm joking. I don't see my slides. That's the thing.
You can use it if you.
Websites. I like third, I think.
Huh?
I think I'm third.
So you can use this one or this one. Yeah, it's up to you. Would you like to use this microphone or this microphone?
I'm too excited to.
Okay. Yeah.
I will do it like this. If this is fine. Okay. Otherwise, I scream.
Oh, let me grab those papers. Your warnings. Yeah, that should work. In theory. Okay, don't worry about it. All right. Hmm? Yeah, you ready? All right, welcome our first lightning talk.
I wait that it's a little bit. Everybody settle down.
Have a seat, and we're going to start.
You're eating in my 5 minutes. I'm going to extend it. Okay, joke. So, it's a lightning talk. I know I'm the first one, so I have to hurry up. So, my name is Engin Diri. I'm working as a senior solutions architect at Pulumi. That's enough about me. And let's start. So, imagine you are part of the platform engineering team, okay? The super platform engineering team providing for your customers a service. That's how it should be. And then you probably also know about this, you know, like treating your infrastructure, your service as a product, and then having some kind of IDP. So that should not something new for everybody. If then, yeah, you should visit some additional talks here at KubeCon and at the Colo days. Okay, so now you imagine platform engineering team working, providing service, customers, and this could be a potential application. So here, let's take the Potato Head application because it's a microservice architecture and has a lot of stuff going on. So imagine this is something you want to expose or you want to provide a service for the people to deploy the application actually. So first up, you come up with this kind of structure, you say, okay, let's use customize, and then you have a lot of YAML files lying around for every service, for every part of this, so a lot of stuff going on. Or you could, why is it not working? Or you could run everything into one big manifest file, and then the attention is on the line, even for this kind of application, you have something like 200 lines of code going on. And then also this version of, hey, wait, Engin, there's something, what about Helm, And then, you maybe come up with this kind of Helm stuff, again, for the potato head application. And then you come into the situation like, it's YAML now enhanced with some magic of Go and so on. And then you're like, wow, that's really, so that's something. And now comes the point, you say, okay, modern problems require a modern solution, or as I would call it here, this solution to say, okay, I have to decide between YAML or YAML in cool, that's the thing. And now we come into my talk actually to say, okay, beyond YAML, building platform APIs with Chrome. Okay, so Kubernetes, that's the base. We are in the week of Kubernetes, so I'm going to talk here a little bit about Kubernetes. And we all think it's great, that's Kubernetes is the best thing. Oh, I guess to speak too quick. So what we're going to do with Kubernetes then to say, okay, there are some things in Kubernetes, for example, the Kubernetes API. And we all know there's a nice way to extend the Kubernetes API called CRDs. So very little small, so I created here a simple CRD, like an application. And then I can start to define the stuff in the Open API specification. So it's really, depending on how you create this, it's very, very big. And I rarely understand this. And thanks to LLM and this stuff, I maybe be able to do this. At the end, you come up with a short form, your CR. You defined now a new object. You extended the API. And now you can use this. But here comes the point. Just by extending, nothing will happen. You can apply this kubectl apply or Argo let's go, but nothing will happen. So what do you need now to make this happen? What do you need now to create this nice abstraction you create? So you could use Kubernetes operators. The most famous ones you may already know, or you tried, or you have it already installed. How does an operator work? It watches now your custom resources and say, hey, somebody created from the CRD a custom resource, and now I have to do some action, and the thing starts. Another one, I know I come to Crow. Okay, oh God, 1 minute. Okay, another one is crossplane. So with crossplane, you can also define your custom resources, XRD and all this stuff, and then a lot of things going on, and you're like, wow, I need to create some stuff. I need to deploy additional controllers. And now we come to Crow, which is actually the main thing of my talk. So the Kube Resource Orchestrator, it brings its own annotation here. You can create now in the resource graph definition, you can create now your CRD, very easy to use. And then, as you can see here, the benefits, resource group bundles related resources into a reusable abstraction, easy to author your CRDs. Dependency aware DAG, so it creates, depending on the stuff you stick together, it creates now a DAG about this, and it can handle more than 6-7 resources. Okay, no, nobody gets the joke. Okay. Okay, and then I get also an application here. The API version is Crow, very nice. Okay, so now comes the point, Engin, why are you talking about this? Yes, I'm working at Pulumi. We have a Kubernetes operator also. So that's the situation where I say we can now attach our Kubernetes resources there, and we can also provide people, because our operator doesn't have the functionality, a nice way to create abstractions. There was already a talk today. Carlos tweeted about this, so this is fresh. Look at this if you want to see a little bit more in action. This is the link, and you can meet me at 104.5 or whatever in KubeCon. I will be there at the booth and give out T-shirts. And yeah, follow me, and thanks for joining my talk.
Great work. Great work. All right. The next one up. You're going to use this? Ready? And go for it.
Okay, so hello everyone. Today, we are presenting the quick 5-minute talk on Dragonfly. So how many of you heard the word before? Okay, so many quite enough. Okay, so starting with, I'm Aditya Soni. I'm one of the SRE working at Forrester and CSM Web Ambassador too.
And I'm Ritik, and I'm a platform advocate. Of time to load. Work large registries, large images and remote registries all together. That is
Just runs a daemon set, so it will be running on each and every node. If you want to
Yes.
So to make it short,
end to end. So if it detects that there's a service running on a machine, can do horizontal scaling and not just a single VM. I want to swap out Telegraph for the OTel collector, and I want to explore some more use cases like having better support for observability in a SIM, or better support for database observability and better SIM support. 3 or 4 lines of YAML underneath a host in Ansible, run the playbook, and it works. So if I go to the black box dashboard, here I can see all the individual endpoints I have, all of the latencies they have, their last status, and what their uptime is over the duration inside of the dashboard. Another cool thing too is that I have kids and I want to make sure they're not going to inappropriate places on the internet, whether that's the hub that's not GitHub or online gambling websites. So here I can actually make sure that gambling websites aren't accessible on their network. where traffic is exposing metrics.
Once from the SIG Romanian, but that
Yep. All right, so I'm doing this on hard mode because my voice is almost shot and my laptop battery is almost dead, and I'm doing a live demo, so this is going to be great. My name's David. Title of this talk is What If Upgrading Kubernetes Was Easy? So you can see here, this is my production Kubernetes cluster. You can see it's production because it says prod over here. And it's got 2 nodes in it. It's a very large Kubernetes cluster, very important. And it's a little bit out of date. A few versions, I think. But it's running this really important cron job. You can see that it's got this cron job that's running on there. It's been going for a long time. And it's really important to me. I want to make sure that it doesn't break or anything like that. So, but I do want to upgrade because I hear that like upgrading is good for security or whatever. Again, this is just going to be a minor version bump. I'm going to go from 1.24 to 1.25. That's not a big deal, right? Like minor version bumps, nothing ever goes wrong there. But just in case, I figured, you know, maybe I should test this thing out. I wrote this cool project called SimCube, which is a simulation environment for Kubernetes that lets you test things out before you deploy them in production. So let's go ahead and do that. So I'm going to switch over now to my simulation environment. Okay, so this is exactly like my production environment, but you could see that it's running a slightly newer version of Kubernetes here, and it's got a bunch of additional nodes in the cluster. These are actually fake nodes. They're powered by this thing called Quack. That's not important right now, don't worry about it. But I'm going to test out my upgrade. So what I did, actually, is I collected a trace of all of the things that were happening in my production cluster, and I'm going to go ahead and replay that trace in my simulation environment right now. We can take a look at that if you want. Let's clear that out. We don't care. Okay, here's my trace. You can see, oh, I've got a cron job in there. Cool. So let's go ahead and apply that. Don't worry about the command line arguments, they're not important right now. You can see that I'm running this actual simulation right now. It's initializing. Let's go ahead and check out what's actually happening. All right, so I've got this simulation driver pod that's actually running my simulation. All it's doing is it's replaying all the events from my production cluster. Oh no, it failed. What went wrong? Okay, well there's a stack trace. That's not great, but we can look through here and you can see, oh, it didn't find some requested resource. It was trying to apply, the cron job was v1 beta 1, and in 1.25 that thing got deprecated, and now now it only supports v1. So I think I know how to fix this. I'm just gonna test this in my simulation really quick. So let's go back over here. I'm going to, so I fixed the trace that I got from my simulated cluster. We can go ahead and take a look at that if you want. You can tell it's fixed because it's got the -fixed flag there. You can see, oh look, it's batch v1, not batch v1 beta 1. So let's go ahead and try to run that one now. All right. I don't think I put that in the right spot. Let's go ahead and put that in the right spot before I try to run the simulation. There we go. I'm using up all my time because I don't know how to type. Okay. I've got 1 minute left. Let's see if this works. Okay, cool. I've got this new simulation that's running. It's called testing 2. It says it's initializing. Hey, there's a new pod that's running. We can actually go ahead and look in, it creates this virtual namespace inside my Kubernetes cluster, and I can see that there's now a cron job in there. It's running, and you can actually see, well, it hasn't actually started any pods yet, but this is all in my simulation environment, and I can see that, I found an issue, I fixed it, and now I can go upgrade my production cluster to 1.25, which I think is the most recent version, right? I have stickers. Come talk to me afterwards if you want. Thanks.
Right. Okay, now I get to plug stuff in. That concludes our lightning talks for the day. Thank you all for being here. Whoop. I'm now going to share a few words with you at the end of the day here. Let me get plugged in. Sure. I still have a USB thing here, so I'll keep it all together. Okay, so I'm Duffy. If you haven't met me already, it's very nice to meet you all. When I'm done with this talk, I'm going to have you all kind of come here toward the front so I can get one big selfie with all of us and make it look like a huge group. I really appreciate you all being here all day at Cloud Native Rejekts 2025. First, I want to say thank you, not just to you in the audience, but also to all of the infrastructure. As infrastructure engineers, I think we need to spend more time thanking the people who build infrastructure for us. So thank you to all the people who are responsible. And thank you to Hippie for being our service provider for the theater here. Pretty awesome. And here are all the people who actually also volunteered. This is a volunteer-run event. Thank you to everyone who is on the volunteer team as well. And also, whenever you go to the Rejekts website, you'll be able to see the opportunity to do all of that stuff. So please volunteer. Next part I want to share with you is this idea of a time capsule. Somebody shared this with me recently, and it really stuck in my brain. And the idea is that the people around you right now, look to your left, look to your right, look before you, look behind you. The people around you are building an image of who you are in their head. And they carry that with them. And when you see them next year, and we're in Amsterdam, or you see us next year, we're somewhere else here in the US, you get to relive that image, that picture of you that's in their head. And that is such a powerful gift, right? Especially in this time of chaos and disorder and disillusionment and despair and all of the other terrible Ds. It's such an incredible gift to remember that we're here together, that we get to actually have that experience and that we can carry that forward for each other, right? And I know that every one of us really brings a lot of intention to that when we come to a conference. We're going to show up, we're going to be present, We're going to bring our best selves, and I'm grateful every day that I'm here at the conference that I get to see your best selves out here. So thank you for being here. This is the most recent one. I believe this was in, actually this might be Salt Lake City. Yeah. So this is my picture of many of the people who are here in this room. So thank you so much for being here. I'm also going to remind you that this week is about this type of connection. So this is that you learned today. I don't need an answer, but I want you to think about it. And I want you to think about it every day while you're at the conference. What was something that you learned today? What was something that you helped somebody else understand today? What was something that you taught today? Right? And this is just a great mindset, a great framing for every day while you're here at the conference. Who did you meet for the very first time today? Right? This is another great, incredible opportunity. Like one of my absolute favorite things is going to a conference in Europe and getting to meet so many people that just never come to the US for very good reason. But really having that opportunity to actually meet those people from everywhere. And finally, I'm going to leave you with this thought, this idea of framing. The idea of framing is we can always look at a problem as a reason to stop trying. We can always think that everything is insurmountable, that everything cannot be done, and we're in a place where we can't move forward. But we can also see it as an opportunity. Right? Everything that's happening around us, we can go vote if we're in America, right? Like we can go protest peaceably wherever we are, right? But we can also just apply this more directly to our day-to-day lives. I'm having a problem, right? I'm having a problem with solving some particular coding challenge, and I can't get my head around the problem, and I can't figure out what the solution is. This can be a way to ruin my day. I can spend the rest of my day feeling terrible about the fact that I can't wrap my head around it. Or I could take a minute and explain that problem to somebody else. This is called rubber ducking. It helps you get your thoughts in order, in a different order, because you actually have to explain them to somebody. That somebody else could be ChatGPT. It really doesn't matter, right? What's important is it gives you a chance to reframe your thoughts. That framing gives us the ability to rethink the problem in a way that is more organized, and we can and very, very commonly, we're able to see the problem through that new light and solve the problem. Take the opportunity to reframe your thoughts in this crazy time that we're in. We're here in it together, and I'm really grateful that we are. Thank you. Come on up, let's get one big selfie.